of you. Today will be an ASMR reading night of science. And what science, you might ask? Yes, the analysis and qualitative effects of large breasts on aerodynamic performance and weight of a Miss Kobayashi's Dragon Maid character. This is a very educational stream. I will be teaching you the science that your government's curriculum failed to teach you. Abstract. A computational fluid dynamics methodology is used to study the salient flow features around the breasts of a human figure and to describe the aerodynamic differences imported by their geometric presence. Oh my god, I can't stop laughing. I'm sorry. Sorry, I need to calm down for a moment. Sorry, this is so funny. I can't take it seriously. This is a serious science article. That's right, it's a very serious science article. Oh, I hope the audio is okay, by the way. Feel free to complain about the audio. So, 2 models are proposed for examination. A 3-dimensional reference based on a character design with a significantly buxom figure. A modification of this design where the breast size is reduced significantly. What in the world inspires this cracked stream? The desire for knowledge, the thirst for knowledge, the curiosity of man. The negative mode made the article into dark mode. Incredible. Yeah, because I think in ASMR a lot of people listen to them on their way to sleep, so it's better if the screen isn't too white. Monsters is definitely. The 2 models are tested at speeds ranging from 1 to 30 meters per second using Reynolds average Navier-Stokes. Drag, lift, and skin friction forces, along with turbulence kinetic energy, are investigated and compared between the different models. The present results are expected to provide useful information on the validity of the statement, "Flat is justice." Yes. In terms of an aerodynamic standpoint, have you ever seen a scientific paper with such a noble goal as to prove that flat is justice? Hi Sakamoto-san, welcome to the science stream of all time. In addition to this, the results can offer worthwhile data investigating the anthropometrical presence of large breasts on sport aerodynamics. Hi, third party. First thing you hear on opening the stream is flat is justice. It's not me, it's not me, it's N. Rabino. It's N. Rabino. Please. I'm just reading science articles because I love science. So scientific, so true. Like, computational fluid dynamics is serious business, guys. It's a complicated field. It's a very important field. The moon is flat, Cuthbert. Introduction. The aerodynamics of the human form has been an area of valuable research in various aspects of sports and competition. Air resistance, hereinafter referred to as drag, is a concerning factor in many time-based trials. Yes, so true. And enhancing potential efficiency can be done through the elucidation of the flow around the human figure. And guys, next time you make a professional sports team, please make sure to limit the breast size of your, team. Yes, to get the most chances of success. Yes. You're ready to learn. Many variables and permutations. Yes, we're all very science coded here. Studies concerning the drag of the human body using wind tunnels can be found dating back to the 1920s. A small sampling of subsequent studies exploring the effect of drag covers areas such as running, cycling, skiing, and skating, all of which reinforces the relevance of aerodynamic investigation on the human shape in regards to performance. In many of such studies, the authors seek to investigate the effect of positioning in relation to drag, and some utilize numerous subjects of differing anthropometric proportions to describe a generalized result on such positioning. Hitherto, none within the author's investigation has described the effect of physiological features on aerodynamic performance in great detail. See, that's how you contribute to the scientific knowledge of the world. You have to do something that someone hasn't done before. See, none have gone into details on the important physiological features that are part of humans, very human features. We don't know yet. Maybe larger breasts make you incredibly aerodynamic. Yes, we're here to find out. Let's not jump to the stemming from certain internet communities. And pertinent to the current era comes the succinct statement, flat is justice. Certain internet communities. Yeah, surely that's not, the vtuber community. Surely. That's not, they're not talking about us, right? Oh no, I was supposed to be. I planned this to be a serious reading. I thought it would be funny if it was such a weird subject, and I took it super seriously and I read it very seriously. But that was the plan, but I I can't stop laughing. I can't do it. I can't. He's laughing at us, yes. The laughs are the best part of ASMR. No. Hey, boobs. So true. Which consequently begets interesting debate that can reverberate and diffuse throughout media. Essentially, the statement describes the appreciation of flat-chested woman. Flat-chested woman. Flat-chested woman. Which posits a peculiar aspect that has yet to be fully explored in human aerodynamics, namely the effect of breasts in regard to drag and overall aerodynamic performance. See, aspect that has been yet to be fully explored. This work is intended to contribute to the understanding of how large breasts can affect the dynamics of the human wake through the use of computational fluid dynamics simulation tools. This preliminary work focuses solely on comparing the relevant effects of large breasts of a selected human design to that of the same design but with, euphemistically, lesser tracts of land. Oh my god, this author certainly had fun with the phrasings. Keep in mind that so this is published. They knew what they were doing. The following sections will present an overall understanding on the human wake in relation to simplified geometry, along with engineering applications, introduce the chosen human geometry and models, relevant boundary conditions, the governing equations, and the numerical methods used to solve the equations. An in-depth review on the computational uncertainty is described, following with extensive results and discussions, conclusions, and recommendations for future work. Yes, a new and wonderful day at the office. I am sure I'm not expecting any papers on the aerodynamics of law. Imagine the face on that guy or girl. Simplified geometry. Hey, you have simplified geometry as well. Hi Kai, welcome. Is this peer reviewed? It's in Science Direct. The keywords: computational fluid dynamics, ANSYS drag coefficient, human aerodynamics, SST. Gibson model. Oh, this is a turbulence model. If you're curious what this is, usually in CFD programs you can choose what turbulence model you pick, and some of it is more accurate than others, and some are more applicable to other depending on how open the space is than others. Model anime, Quetzalcoatl, titties. What are these keywords? What are these? Why it isn't Science Direct? What are these keywords? What are these keywords? Who will search for these keywords? I can't. I'm gonna die. I'm gonna fucking die. Thank you also for the follow, guy. I can't. Oh wait, I meant K Omega. Sorry. Yes, the human body can be best described as a bluff body in respect to the flow around it. This is how you get teenagers interested in science. Literature on the behavior of the wakes behind bluff bodies indicates that the flow will be unsteady due to the turbulent transition and separation of the boundary layer. Yes. A simplification analogous to the human shape can be represented by a grouping of uniform circular cylinders, and therefore existing studies on this type of geometry can provide general insight into the wake region. A tiny spoiler, there will be 3D models later on. This paper is cited by another paper. Please tell me what paper cited this paper. We need to find out who was the most hydrodynamic. True, we need it. We need to know who to hire for our professional sports team. Summer et al. Described the wake and development of vortex structures of cylinders with aspect ratios, height to diameter of 3, 5, and 9, and determined that a transition in vortex shedding occurs at height to diameter over 3. That one. What is this? What is this? The picture of the guy of that paper looks so smug. The citer you. An investigation by Okamoto and Tsunabashiri also supports this finding, adding that cylinders with an aspect ratio of 3 experience a recirculation region that extends 4 diameters downstream. Recirculation regions are actually one of the problematic things in simulating wind tunnels in like computational fluid dynamics simulations, because recirculation areas make it hard for your residuals to go down. Usually the simulation, you want your residuals to go down because you want the values to converge to a value. Yes. I am saying science. Trust me, I'm an anime girl on the internet. I know about computational fluid dynamics simulation. Trust me. She did her research. Actually, I did not. Otherwise, you get floating point errors. Yes. Those sure were some words you were saying. Sometimes you don't get errors. Actually, it just doesn't converge. Like sometimes it will be divergent, but sometimes it's just a steady high residuals, which could be from other factors as well. It could be due to the initial conditions you set as well. They could be the wrong initial conditions. It could also be due to your mesh. It's basically very hard to troubleshoot. Computational fluid dynamics is serious business. It's very serious business. Her smooth brain is betraying its density. You trust. Thank you. Assuming the human form takes on a roughly large cylindrical shape near this aspect ratio, it is expected that the recirculation region will behave similarly and extend approximately 4 body widths downstream. Do I have scientific background? The only thing I will admit is the software used in this paper. I have used it before. Yes, I have used it before. Alright. Powerful. We all have a scientific background if you think about it. So cool. A readily apparent deviation in geometry compared to studies done on singular cylinders is the presence of the gap between the legs. Yes! Yes, the side gap. Oh my god. Yes. A gap between legs. What is this paper? What is this paper? Yes, an extensive and comprehensive. Reading it off, I saved a PDF file. An extensive and comprehensive review done by To and Alam on the various arrangements of 2 cylinders indicate the wake structure falls into a multitude of regimes. They were trying so hard. You're impressed. I'm impressed too. In a side-by-side configuration, being similar to the 2 legs of a human, it is deduced that there are 3 primary regimes where the wake experiences proximity interference. When closely spaced together, when you're thick. The first regime shows that the cylinders act similarly to that of a single bluff body with the widths corresponding to the 2 cylinders. Makes sense. Makes sense. They're engineers. They just like approximating like 2 cylinders. There's just 1 cylinders. You know, engineers and approximations. Am I right? You ask because you just noticed the file name. That's the file name. That's the file name from the website. The file name from the website is r_anime_tts_aerodynamic PDF. That's the file name from Science Direct. You don't have access to fluid sim anymore, but you do have thermal and structural analysis. A lot of the fluid dynamics actually come with thermal simulations, like the software used for this, and this Fluent, it actually has it actually even has a boiling model in it, which not a lot of computational fluid dynamics software have. Like some of example specialized software like Flowterm and other software, they don't actually have a boiling model in them. But there's as I remember, there's like one other software that has boiling models in it. But yeah, this has a ANSYS has a lot of thermal analysis in it. Like there's a lot of thermal stuff. Yes. Which one of our models makes a better heat sink? I don't know. That's gonna depend on your thermal conductivity. Like maybe you have way less mass than me because my brain is so dense, you know. I have so much mass that a human can be rounded to a single cylinder, maybe even half a cylinder. So author approximates the human's shape to a cylinder with true hero. It's so insane. Apparently it's the most read article on ResearchGate. People get interested in science. You're 3 centimeters. Hey, I'm at least twice as long. Yes, your brain. I'm close. When the gap is larger than 20% of the diameter, each cylinder has individual wakes that strongly affect one another and is associated with the second regime. All those views of me. That's how thirsty I am for knowledge. At gap widths exceeding approximately 100 to 120% of the diameter, each cylinder acts as an independent body, with the vortex streets being closely influenced by one another. Seeing that human legs are not strictly cylinders with a fixed diameter, but more akin to inverted tapered cylinders, the wakes behind the legs will likely behave in a similar fashion observed in both the first and second regime. With the ankles and calves being narrower and having a larger gap between them, the second regime is applicable. A transition to the first regime can be expected, associated with the bulkiness of the thighs and reduction in gap width. Engineering literature can also provide details on the flow characteristics around the body. Many of such studies are motivated by exposure control and contaminant transport, thermal issues, and comfort prediction, rather than overall drag effects. Inherently, many of the tested flow characteristics are evaluated in a quiescent environment or at air velocities that are of a lower order compared to those found in sports-related studies. Nonetheless, these studies provide useful insight on the natural turbulence caused by the human form and the expected anatomical location of flow separation. In Savon et al. Utilized a high-speed camera to record the wake generation of a 1/5 scaled realistic human mannequin, a giant anime figure, surely. It was accelerated to a velocity of 1 meters per second. Good evening, Venus. Hi, good evening. Ready? Welcome to science. Where did other 4 centimeters? Hey, I am 7 centimeters of science. Okay. You love anime boob science. Yes, we all love that. Thank you for coming here in the name of science. We are here to explore the Validity of the statement, flat is justice, in terms of an aerodynamic standpoint. Yes, trust me, I have glasses. Lukoa. Oh, I have my favorite. My favorite drill, like a hand drill. My favorite drill. It has a giant sticker of Lukoa in it. And then it's funny whenever someone needs to borrow my drill, I hand them my drill and they see like giant Lukoa stickers on my drill. Yes, it's my precious drill. I really love my hand tools, yes. You don't mind a moral super. Yeah, for sure. You love putting anime stickers on your tools. Breast, that's me too. That's it's easy to know which one is mine. Like if I leave mine in like the fabrication or the metal shop, like no one knows, no one wonders whose drill that is. That's of Urbania's. There's a big anime girl in it. Original reference design. Yes. The modified design proposed for comparison. Yes. Both are good in their own way. A perspective measurement of Lukoa in reference to a door frame using the vanishing point tool in Adobe Photoshop. From their results, it was found that the shoulder undergoes flow separation and produces vortices in a regular pattern. What a wonderful time to be alive. The hands produce a well-defined yet unstable vortex sheet that curls towards the center line of the body. The head acts similarly to a classical sphere-cylinder cases with the addition of a trailing wake forming from behind the neck. The neck was found to remove the expected counter-free shear layer that is present in cylinder studies, and thus eliminates the formation of an oscillating vortex sheet. All in all, it can be said that the observed human wake is a highly complex and richly diverse system that is easily influenced by inherent geometry used. It is expected that from this study, an overall summary can be presented on how and to what degree the previously described flow structures are affected by the presence of large breasts. Methodology. The use of human models affords greater realization of the pertinent flow characteristics as they are considerably different than those of generalized models. So true. Yan et al. Concluded that an excessive degree of simplification in using a mannequin can affect the ability to achieve accurate results and thus precludes the use of a simplified model for the study. However, acquisition of a 3D scanned human model with a significant bust inevitably proved difficult. Posting an ad in your university, like triple D cup-sized woman wanted for science. Please let me 3D scan your breasts for science. I need it for my thesis. Please, you don't understand. I need to graduate. You don't understand. I need to scan your breasts. Let me scan your breast. Your breast, your very big breast. It has to be very, very big. And I have to scan it. Triple D cup size woman wanted for science. You need it for my so true. Who would say no? Imagine writing an entire paper as an excuse to met. What? It's not an excuse. Don't you see this valid reason? It was indubitably difficult to acquire a 3D scanned human model with a significant bust. What do you mean excuse? Look, there's a legit reason. It's very legit. It's very... There's very, very believable justification. Nobody came. So rude. So true. The use of a highly conventional approach was used to ameliorate the we needed to ameliorate this issue. It's the type to order Starbucks. Oh my god, I can't believe the author. Like, you think it would be enough that he just wrote a paper on the computational fluid dynamics of breast? But no, he had to justify it. With how proving getting a significant bust 3D scan is difficult, and they had to solve the issue. They put like a background. I can't believe this. Paper. I'm in awe of this paper. The anime adaptation of Miss Kobayashi's Dragon Maid, being a recently popular show and spawning a sizable subculture on the internet, proved suitable in terms of providing potential models. The dragon characters, themselves being based off of mythically and culturally prominent dragons, assume a human form to interact with other humans in this well-received slice of life urban fantasy. Oh my god, I can't believe, like, this wasn't relevant to the paper. It wasn't relevant to the dynamics of large and small breasts to have to explain that these are dragon characters and they assume a human form, and it's a slice of life urban fantasy that is well received. We're like, what is this guy? Holy crap, this guy. A majority of human forms of the female dragon characters possess significant busts. However, Quetzalcoatl, referred to canonically as Lakoa, hey, that's also a dinosaur, will be named as such throughout the rest of this paper. Hi, welcome, Rura. Welcome to science. Welcome to science. We are here to investigate the validity of the statement flat is justice. Welcome to science. We love science indeed. However, Quetzalcoatl, referred to canonically as Lakoa, will be named as such throughout the rest of this paper, substantiated herself as the adaptation's gag character by her significant size, making her the perfect candidate and providing a suitable model. This stream is like a perfect time. Like me updating my models, eyebrow tracking is such a perfect timing for this model, because like a lot of these things I'm reading make me go, Like a lot of these things are making me yet to provide some context indeed. That's all godless, yes. Being clearly the largest among our fellow dragons as established in figure 1. What do you mean as established in figure 1? Okay. Makoa provides the best contrast between a large bust and having none at all. Yes, we have to exaggerate. We need to look at the extremes for science, to make what we're looking at, more observable. Indeed. To provide the most direct comparison in regards to the effect of large breasts on the wig, a dramatic reduction to the bust size is as reflected in figure 1. For use in this study, in order to obtain accurate results from the setups described later in this paper, it is important to have the subject in question reflect real-world scales properly. Lukoa's height, while in human form, is not given explicitly in any related media within the scope of the author's research. Thus, Lukoa's height must be estimated in relation to objects of which a reasonable measurement can be readily found. Conveniently, there is a scene found within episode 6, season 1 of the anime adaptation wherein Lukoa steps through a door frame. Assuming the door frame is of a typical size, used for external entrances, in addition to Lukoa being scaled properly in the scene, we can estimate her height using a vanishing point technique. This guy really did his research. He really wanted a representative study. Using the door bra as a gig and nerd, so true. As depicted in figure 2 to judge Lukoa's height, it was determined that she stands approximately 177 centimeters. Breast. I'm like minus 25. What the heck? I'm like minus 170. Yes. Yes, ignore what I said. Ignore the other thing I said. I said I'm minus 170. Using scientific power shortcuts, so true. This is the correct method, so true. Legible. What do you mean for someone? Stop. I will ignore all the slander to my height. Problematic height difference. Oops, what did I click? Oh god, we have a long way to go. Using the door along with her horns, boosting her overall figure to a height of 182 centimeters. Hey, you guys are making fun of my height, but I bet you guys are under 182 centimeters too. I bet you guys are also under 182 centimeters, huh? These numbers can be considered reasonable based on canonical descriptions of Lukoa's towering nature compared to the average height of 158 centimeters for that's half. I thought Japanese women were short. Why are they so tall? I thought Japanese women were small. Why are they taller than me? Why is the Japanese average Japanese woman taller than me, huh? Including ears. Nah, you're so tall. Nah, I bet you're so small. You guys are so small. You're probably all so small. Since Lukoa is a fictional character that is commonly portrayed in a two-dimensional world. Two-dimensional. Determining her form drag between the two proposed designs as described in Figure 1 requires that we add another dimension to her model. Conveniently enough, an available 3D model of Lukoa was used that would make the simulation possible. This Miku Dance 3D model, henceforth referred to as the normal model, was then imported into the 3D modeling program Blender, scaled to the determined height as described in the previous section, then exported into an STL file. This STL file was then repaired using the built-in repair feature present in Microsoft 3D Builder due to the unclean geometry inherent with a model to achieve the modified design, henceforth referred to as the flat model. The original Miku Dance model was modified using the built-in tools in Blender to dramatically reduce Lukoa's breast size. The export and repair process remained the same as for the original model. MMD to STL is actually insane. Someone out there when reviewing this paper looked up Dragon Maid and MMD is so true. The author just conveniently had this model in hand. Conveniently. Someone out there was never the same for that day. Sure. When Vinya finds out Japanese women are taller than 7 cm. What? I can't believe this. Japanese women can place me on their shoulders. I can ride Japanese women on their shoulders. Average must be a lie. So true. Yeah, that's actually one of the what do you call this? One of the benefits of depending on the CFD software you use. Like this person, they used ANSYS Fluent, and ANSYS Fluent, the mesh system, allows you to import 3D models. Because like some computational fluid dynamics software, that use a different type of mesh system. Some of them like use like a cubic system. So if you try to import the Lukoa model, it will be voxelized. So yes, the author certainly picked the correct computational fluid dynamic software for this specific scenario. Yes, they picked the CFD software that had the appropriate mesh system in order to most appropriately capture the curves of the breast. Yes. Riding the shoulders of the giants. Hot. Need to draw that. It reminds me of do you guys know that fan animator for HoloLive in YouTube, and the only thing they do is make animations of HoloLive girls but giant women? You know who I'm talking about? They make like 2D animations that are actually good, but all of it is making them giant women. Petition for Opabenia plush that can be affixed to your shoulder. Oh my god, there's a great idea for that. I have a plush like that. So guys, you know I love Potato Corner, right? I love Potato Corner. The official Potato Corner plushie can be affixed to your shoulder because there's a plushie. The plushie has a magnet inside and it comes with a magnetic disc. And what you do is put the magnetic disc under your shirt and put the plushie on top of your shirt so that it like clamps on your shirt on your shoulder. It's such a genius merch idea. Like, it's such a genius merch idea. Why aren't there VTuber merchandise that have like a magnet to put on your shoulder? I'll be the first one. I think you recall this, not in the slightest, but you need a channel name for no particular reason. I think it's Alice Magic. Let me search Alice Magic YouTube. Hold on. Yeah, it's yeah, it's basically filled with like you know, Godzilla-sized Hololive girls, and their animation quality is actually really good. Alice, oh no, oh my god, Alice, my beloved, Alice, my beloved VTuber. Now you're custom ordering this and patenting it and stealing it. Good luck with no one buying it. I wonder where this is. 1 centimeter. I'm gonna. How do I? Chat warning. Slander. Send warning. There. I sent a warning to you, Seiki. I hope you received the warning. Shown in figure 3, all the positions between the two models remain the same, and the left unperturbed to leave the reduction in breast size is the sole geometric difference to be investigated. Yes, yes, control your variables, very science, yes. That's how you do experiments. You can, yes, very scientific, yes. Control the breast size. Although the typical or orthostatic standing orientation of a human has the upper limbs in where the relaxed position, the arms are left posed. Yes, T pose for yes, at a 45-degree adduction angle from the torso, as this is the default A pose when importing the model. I like how I thought they were gonna have a justification, like they had a dramatic justification for why they had to pick Lokoa because they couldn't find a real girl, but here they're like, it's just a default pose. This paper sure is alright. Literally 1984. No, it's literally the Cambrian. This arm position also has an advantage in this study as it potentially enables a more thorough analysis on the effect of breasts on the wake region, whereas a neutral... Oh, there's the justification. Oh, there's the justification. Whereas a neutral standing posture would have the arms interfere with the downstream effect of the breast. There's the justification. The hair is left modeled as a solid to reduce simulation complexity and setup. When you have a great idea because of Lokoa's assets, but you don't want to learn to work right. The left hair is left modeled as a solid to reduce simulation complexity and setup. If it's MMD, it should be rigged already though. While humans naturally lean forwards against the direction of the wind to maintain equilibrium, this factor is not considered in the study, as this leaning would change the frontal area exposed to the fluid flow and thus complicate comparisons against static reference models. My god, so much justification on why he should not put a lean, why he should just use the default import pose. Look at it, it's you know, it's do not change the frontal area exposed to the fluid flow. Yeah. For comparisons again, static reference model. Yeah. This. Oh my god, I can't. This guy. I can't. This person. This guy is such a legend. I can't believe it. It's like. Oh my god, there's paper. Like it's nothing is boring. Like every paragraph has something new and interesting in it. Like this paragraph, like I can't believe it. I could use a Google Mouse. Hey, let the guy and his waifu. Dimensionally, the bounds of the two models are similar, with a height and arm span being 1.82 and 1.387 meters respectively. The normal model has a depth of 0.525 meters, whereas the flat model is only 0.414 meters. The frontal projected area, A, of both models is 0.584 meters squared. The volumetric difference between the two is 9.19 liters, indicating that each breast on the normal model has an enormous volume of approximately 4.6 liters. Yeah, where are you gonna find a real woman who would let you scan her breasts, who has a volume of 9.19 liters of chest volume, huh? Why did we need to know the volume? I know, right? Like, why do we? I am looking incredibly disrespectful. The underbust circumference of the normal model is approximately 64 centimeters, and the bust measures 115 centimeters. It's important because I can't. It's like, and the bus measures 115. Oh my god! Oh my god! Oh my god! I know. Oh my god! Oh my god! I know why they got the volume in the bus measurements. It was to get the cup size. No, they didn't. Are you okay? No, I can't. This paper. Apparently, the average breast volume is 650 milliliters. Oh god. Attempting to match the dimensions and bust volume of the normal model to existing cup sizing scales is difficult, as these measurements are exceptionally large and exceed volumes measured in other studies. LS 4006-1998 scale and extrapolating cup size from the largest listed cup size, the I cup. My god, they even extrapolated their cup sizing because because the scale wouldn't fit in the known scale. They had to make their own scale. The normal model can then be described as 10 cups larger, an estimated as 65. The flat model is a stark contrast to this, where it matches a petite AA65 size. Please kill me. Please kill me now. this is a fun tangent, but you know Sheena from Face Connect, she recently had her cup size measured at a store, and she's double A. Yes, this is Sheena. This is Sheena cup size. Sheena is the peak Face Connect body form. Yes. Meemaw moment. Yes. For such a little girl, you're like someone got her some candles. Anyway, you're going to sleep. Yes. Good night, Tamban. Thanks for stopping by. I hope you dream of S65 and S65 women of your dreams. The dramatic difference in bust size between the models serves to provide the most significant change in outcomes. It is assumed that due to the absurd bust size, any size smaller than the normal model would have an outcome that would fall in a range between both models. Sorry, blowing nose ASMR, disgusting. I'm so sorry. I'm so sorry. Evaluated metrics and implementation. 4 metrics under investigation for the study include drag and lift forces, including their associated coefficients, skin friction coefficient, and finally, turbulence kinetic energy. You can't clip it. I disabled clips in the options. Haha, I am unclippable. Haha. You get the average lot and regular coil. You pretty much get an icon. Yes, to evaluate the drag coefficient, C of D, and drag force, F of D, the following equations are used. Yes, the drag coefficient is equal to 2 times the drag force over density use of infinity squared times A. Yes. Here, physics is beyond the scope of the author and doesn't study. Oh, this was for another note. Man, we should read the subnotes for. Yes. F sub D is the integral of negative B cosine theta plus I forgot how you say that. Sine alpha. Yes, you integrate on the air. Yes, very smart. Oh, it says here. Screen tiny set calculus. Don't worry, the program does it for you. No need to. If you're an engineer, you don't need to calculate this. This will do it for you. Yes. Where rho is the fluid density, U sub infinity is the free stream velocity. Yes. A is the frontal projected area, and P is the pressure at the surface. Oh, yes. You don't need to calculate anything if you use cylinders. I mean, the hair wouldn't affect aerodynamics that much anyway. I mean, it's important that it's constant between the two models, and you're right, it's already downstream. So yes, that's true. Also, Omega, you're crashing out. You're so glad you never had to do fluid dynamics. Yes, tau sub omega is the local wall shear stress, where mu is mu with oh my god, why are we doing so science? Yes, the dynamic viscosity times, with the flow velocity along the boundary layer. Y being the height above the boundary, the value of C sub d is not constant and is dependent on Reynolds number, which is defined as Reynolds number, where L is an arbitrary characteristic length. In this study, L is equal to the height of the models. The lift coefficient is comparable to the drag coefficient. You're learning. Being that the force is evaluated in a direction that is perpendicular to the mean flow direction, vertically upwards, thus, yes, the lift coefficient. Yes, class, it's time to memorize these equations. You will use them in the exam at the end of the stream, so make sure to memorize how to calculate the lift and drag coefficients. Instead of the frontal projected area A as a reference surface area, S is used. For consistent comparison, however, A and S are left defined as being equivalent, thus A equals S. This result does not affect the calculated forces, but rather only the coefficient, and as such, the lift coefficient is dependent on the frontal area. The skin friction coefficient is evaluated in a similar manner to the drag coefficient, since the force attributed to skin friction is a component of the profile drag F sub d. Therefore, yes, it's the same as a while ago, but this time, yes, we used we used the one from the shear stress. Yes, I'm failing the test. Is it too late to switch majors? Yes, it's too late. You can't switch majors if you're kicked out because you failed the exam. You have to pass first. Analyzing the skin friction coefficients allows insight into areas where the boundary layer thickness changes. As turbulent flow increases, the thickness of the boundary layer increases, and consequently, areas where C sub f transitions to larger values or experiences spikes are indicative of where flow separation is prevalent. Turbulent kinetic energy signifies the loss of kinetic energy from the mean flow and represents the energy present with eddies in turbulent flow. It is a direct measure of the intensity of turbulence. In a general form, quantifying the mean of turbulence normal stresses, TKE is defined as... Yes, it's time for you to memorize the turbulent kinetic energy equation to... just what you'll take a look. I always saw that meme from Gigi. We learned that S65 is approximately 10 sizes bigger than... No, you're wrong. No, so you failed the test. It's 10 cups larger than I. Or is it? I love that meme too. Like, I didn't care for the meme because it was by a three-doid male guy, and I don't like having 3Ds three-doids in my feed. So I didn't care about the meme, and I'm when Gigi did it, I was like, yes, I care for this meme. It also Fletcher's man. The exact value of TKE is calculated based on the closure of the Reynolds average Navier-Stokes equation, which is further discussed in section 3.3. Hi, welcome, Adan. Welcome to our science stream, where welcome. Here we are investigating the validity of the statement "flat is justice" using computational fluid dynamics. Yes, we will be simulating flow along with its boundary layers in order to simulate a turbulent flow, in order to be able to quantify the drag on this perfect model to use for science. You exported your model into Fusion 360. We will find out if flashes or high speed low drag. Where were we? The numerical simulations present in this work, along with the automatic evaluation of the equations described in this section, were carried out using ANSYS Fluent R17. The 3D models defined in section 2.2 were imported into Fluent and followed the methodology as described in the following section. Yes. Oh, if you guys have potato computers, like I think ANSYS Fluent has an option where you can like outsource the computing to cloud, but you have to pay extra for it, and I think it's really expensive. But ANSYS has other software for simulations as well. I think they have some like student friendly software, although I haven't. Yes, so that you can also, even if you have a potato PC, you can use their simulate to cloud to replicate this study. You know that methodology is important for research paper, but also I feel like I'd be lazy and like I throw it in the software. Here's my settings. I think that would only work if you auto-generated the mesh. It's incredibly easy to borrow SolidWorks, which isn't bad. Yeah, SolidWorks is an entirely different thing. Like, I know in SolidWorks, I think it has a pretty good integrated simulation for like stresses, structural analysis, but it's like an entirely different beast from ANSYS. Like ANSYS has like is a full-on thermofluid dynamics. It's been stresses, not fluids. Yeah, but yeah, SolidWorks is it's really fun to simulate the stresses. The music actually finished. I'm actually most used to I want to get used to SolidWorks, but I'm like, the workflow is super different from Creo. It's so weird to jump between CAD softwares, like especially like I think like I tried Fusion 360 for a while, so when like I cannot it doesn't have like the feature the feature tree system, like the one in Creo, and it's so not intuitive for me. I've been using Fusion instead of SolidWorks for the last 6 years. You can use MS Paint. Very important skill. SolidWorks looks cool and fun. It does. The use of boundary conditions based on real-world environments enhances the overall applicability of the results stemming from simulations. It was therefore important to determine the most appropriate and accurate environment in which to simulate the models with. It was found that the overall location used in the animated adaptation of Miss Kobayashi's Dragon Maid was based on the city of Koshigaya, situated in the Saitama prefecture of Japan. You know, when he starts putting context like this, I have no idea what to expect with the next sentences. I'm like, why is he giving us all this info? Where could it go? This paper is so riveting and exciting, you never know what happens next. A logical time of year to assume a person being outside without excess clothing would be sometime in the summer. Using the months of August, it was found that the weather conditions in Koshigaya and nearby surrounding regions feature averages of 22.6 degrees for temperature, 73% for relative humidity, and 1005.9 pascals for local atmospheric pressure. Thus, the air density was calculated to be raw equals 1.1581 kilograms per meters cubed, and the dynamic viscosity to be mu equals 1.86847 10 to the negative 5 kilograms per meter second. Please kill me. I gotta know if flat is justice. This is the most usual shit process. I know. I gotta ask, what was this fella trying to prove? Bro, it was right at the intro. This is all about the validity of flat is justice. This is all about, is flat justice? Is flat justice? It's a very noble thing to prove. You're supposed to write papers with enough detail that you can defend it. I can't believe this. This guy, he could just say put an average, the average value of room temperature, standard value of air. But no, he's like, what city was the dragon made? What time of the year will she wear a tank top outside? No, he has to. But gotta be accurate. This is science after all. Yes. Of course, you need the dynamic viscosity. That's important in calculating the Reynolds, as we saw. Hey, where did that go? A while ago. See. See, we need that. It is very important. See, we needed the dynamic viscosity, because without that you can't get the Reynolds number. And if you can't have the Reynolds number, how are you supposed to know what regime the air is, whether it's laminar or turbulent? It's very important, very basic. Hi, animals. Let's calculate. Welcome to science, animal. Welcome to science. In this paper, we are. The main purpose of this stream is to explore the validity of the statement "flat is justice" in an aerodynamic standpoint. Have you ever said flat is justice? And has your parents ever told you, what's wrong with you? Get out. Stop living in my basement. Stop saying shit. And they didn't believe you. But now, next time you say flat is justice, and your parents become disappointed in you, now you can prove them wrong. You can tell them they're wrong. All right. We don't know. See, it's very important. Very important. I think you said flat is justice since you were 12 and based. Brain volume is like 1.45 liters, not even deserve a single. Good night. Good night, Kai. Thanks for stopping by. Good night. Thank you so much. The situation is very specific. No, it's a very no, it's not specific. It's a general situation that a lot of unfortunately, a lot of people these days are stuck in that situation. They're ridiculed when they say flat is justice because they don't have enough science to back it up. They don't have enough science to back it up. That's what we have here. Yes, since the human body can vary based upon clothing worn, surface roughness, and effects of fabrics are parameters that are ignored in this study. Although multiple studies have shown fabrics have a noticeable effect on the overall drag of a human body, the walls in this computational work can be regarded as smooth. In all simulations, the models and ground of domain are modeled as non-moving walls with no slip conditions. The clothing that is part of the models is treated in the same manner. Yes, of course. Makes sense. Yes. Your walls aren't closing in on you, literally, are they? Maybe they are. Summary of boundary conditions present in this study. The wind speed. Yes. Yes. The Reynolds number, the domain bounds. The turbulent intensity. The turbulent viscosity ratio. The outlet gauge pressure. Where is the outlet? Yes, it's a wind tunnel basically. Blue is the outlet. Symmetry in yellow. Yes, this is actually a typical wind tunnel situation. Yes, wind tunnels are used to, you are used to like calculate, yes, how aerodynamic you are, to measure how and there's actually wind tunnels are like a thing in real life. They're actually like, this is simulated, but wind tunnels actually work like this in real life. Literally, there's a tunnel of wind and then you put something in it. And there's also wind tunnels. There's if you Google, you'll probably see the gigantic ones where we put a car or a plane in it. But there's actually really small ones that you could place in a room and you can place small objects in them. Yes, wind tunnels are. Shouldn't it happen to your body, Zach, and your other guy, Zach, and your yeah, so true, so relatable. Qatar thing, that's right. All the colors being inverted makes the description hard to understand. Shh. Inlet velocities range from 1 meters per second to 30 meters per second in a positive y direction, since in this respect the positive z direction refers to the up orientation, highlighting typical wind speeds encountered on a day-to-day basis, such as walking, all the way up to standing in a violent storm. Yes, you need your aerodynamics are very important in a violent storm, you know. You need to know. if like you need to, if you're going for a jog out in, the eye of the typhoon, you need to know, like, can your aerodynamics handle it? Put your brain in a wind tunnel and there be no turbulence whatsoever. Yes, you're indeed very smooth. At the inlet, turbulence is specified using both turbulence intensity and turbulent viscosity ratio. Turbulence intensity is defined as the ratio of the root mean square of velocity fluctuations to the mean flow velocity, and the turbulent viscosity ratio being directly proportional to the turbulent Reynolds number. These values are summarized in Table 1. The boundary condition at the outlet is treated as a pressure outlet, where a static gauge pressure is specified. In this case, turbulence is specified similarly as the inlet, but regarded in terms of backflow. Should the flow reverse direction at the boundary during iterative calculations? What? In this case, sir? Okay. The remaining borders of the virtual wind tunnel are modeled as asymmetric to simulate zero shear slip walls. Oh yeah. He put like the quotation on virtual wind tunnel. Yes, because it's usually refers to the real thing, not a fake one. You don't understand 8 out of 10 every 10 words. Don't worry, words weren't even invented in my period, so I don't know any words. I like knowing the words but no longer knowing what they mean when put together. That's even more frustrating. In Fluent, this boundary condition assumes a zero flux for all quantities, which imposes a zero normal gradient across the defined boundary and thus enforces a parallel flow. Yes, that is indeed like the proper condition for a wind tunnel. In Fluent, the flow is initialized with a velocity field equal to the specified velocity for the run. A run specified at 1 meters per second would have the entire field initialized with that value and so on. Yes, this is good practice because the value you initialize at your run affects the speed of the simulation and affects the convergence of your so yes, it's like usually, like, if you're doing a thermal fluid simulation, you actually also initialize at the specific temperatures, but since this time it's just a fluid one, you just initialize at the velocities. Yes. Turbulence parameters at the boundaries are also initialized based on turbulence values as specified in Table 1. The blockage ratio was determined to be 8.7%, which would necessitate the usage of a correction factor to data. However, a blockage ratio of up to 10% in regards to bluff bodies has shown to provide reasonably similar outcomes compared to testing using lower blockage ratios, and therefore a correction factor was not used. You need to get breakfast. Good morning. I hope you have a good breakfast. What the hell, even as a zero shear slip ball. What time is it? There even a secret. she asleep. Don't worry, I have the power of Google on my side. I can do this. It says the no-slip condition indicates that the fluid sticks to the wall and moves with the velocity to the wall. Let's see. Yes, I am. That came from my brain. That didn't come from Google. I totally know this. Yes. Meaning there's no friction or resistance to the fluid's motion along the wall. No tangential forces. I mean, it makes sense if... I think it makes sense if there's no friction or resistance to the wall. It could have just said smooth wall, but it makes sense because if I think it makes sense because if you like generate like if you mess up the like you have a too high boundary layer from too much resistance at the wall, it could mess with the ones coming from what you're measuring. She'd use the tantrum for doxing being smart. Really, you're so smart. Your brain, yes, my brain is Google. I'm so smart. Like it makes sense, but you have no intuition, so you just go. Yeah. Because like especially especially I think like in pipe flow, if you're modeling like flow of like water through a pipe, for example, like if it's the boundary, you know, if it's small enough, it could like mess with each other if it's like big enough. I don't know. I am so smart. Please believe everything I say. Just kidding. Don't listen to me. Don't listen to me. I have no idea what I'm talking about. Look, you don't... The computational fluid domain was discretized with an unstructured grid as shown in figure 5. Where figure 5? Let's see their grid. Let's judge their grid. This is how you judge. This is how you judge someone simulating fluid dynamics. The number one thing you judge them for is grid. Like you see like someone's grid, you laugh at it and say, wow, your grid is so inferior to mine. That's how engineers judge each other. They judge each other with how high level or noob their grids are. Yes. The development of Cambrian telekinesis was inevitable. Figure 5 is killing me. Why is it killing side view of the full grid domain along the median plane? This is just basically what this means. So for people who don't know, the grid, that's like the divisions, right, that have like for the calculations. So basically you want your grid to be focused on the parts where you expect the most changes in the flow. So for example, like the separation of flow, like or in this case it's in the model, right? And we want like enough grids at the back also, because this is where the vortice is, and this is the flow at the back, right? So but here at the front, at the model, we don't really expect the flow here to be just parallel and constant, so we can have like a rough grid here, and that's why it's concentrated at the model and at the back. And here if it's farther away, we don't consider it that important anymore. It could be, so it's basically just the more wide it is, the more concentrated the grid is. Like it like affects the values a lot. It will affect your results a lot. So it's very important to your grid to capture the flow accurately, but it's important also not to like oversaturate it with grid, because your computer will die, and your computer will take like one entire week calculating like one single simulation, and you will be so sad. Lovely, and actually makes sense. Absolutely grid build. Assert grid times, that's right. You rounded pi to 3.1 and used 3D models instead of cylinders. Wouldn't have been there. Yeah. Yeah. Like yeah, the computer I used before to do ANSYS on, I actually just learned ANSYS on. It was actually my choice. I just was like, I'm bored, I want to learn ANSYS. But I didn't actually. It was like my choice to pick it up, but the computer I was using it on had 192 gig of RAM. And it wasn't, and I was sad because I mean, I don't have it anymore, but I was like really sad because I'm in my apartment, right, and I'm trying to sleep. I was in a studio apartment, and it was hard to sleep because this super mega computer, it's like a jet engine. I'm like trying to sleep, trying to watch anime girls, and it's like yeah. And then that computer, I mean, I don't have it anymore, but that computer, what do you call this? The processor is also special. It's not something you'll find anywhere in the market. It's like a very special processor. It's like basically not the kind you can use to build computers. It's like, yes. And I don't think, yes. You heard Rikira's computer idle. It's super loud. My computer was even sadder. But yeah, I don't have it anymore. Yes, it was a very powerful computer. Like people don't know. Imagine playing video games and you have 192 gig RAM, and then when you tell people you're playing with your RAM is 192 gig, they just laugh at you and don't believe you. And I'm like, you don't know my power. You don't know my power. It's a little important if you know what I mean. The real space heater that streams. That's so true. Seeing a processor. Yes, there's a lot of kinds of those. So there's lots of kinds of those. It's one of the like there's like the gold ones, and it's one of the very high parts of it. Like I took like a really long time researching how much RAM do I need, and then in the end, instead of researching an optimal amount of RAM, I was just like, screw this. I'll just like buy as many like as sticks I can fit in this motherboard. Probably run Crysis. It can. Gets a lot of super small computer plays for Fortnite or Minecraft on media settings. Yeah, I remember back then I was like having such a hard time deciding how much RAM I was reading scientific papers on like RAM distribution for Xenon processors specifically. There's like super niche papers studying RAM, like long, super long ass papers. I was even reading those, and then in the end I was just like, screw this, I just need all the RAM. Yes. Yes, add more RAMs. Oh my god. Oh yes. Where were we? Oh yeah, I was talking about the figure 5. I got distracted because to reduce numerical diffusion and to more accurately resolve the viscous boundary layer, the surface grids on the models and ground were extruded using prismatic elements that are sized approximately to the aspect ratio of their associated surface cell. These prisms are grown to 5 layers and follows recommendations put forth by Lanfrid. Oh my god, to reduce this guy, he probably has a weaker ass computer than me. Just kidding. That's why you download a few gigabytes every week. Yes, you have to download them. Download them until you're as powerful as me. 2 prismatic bodies of influence of increasing refinement are used to improve the resolution of the grid in both the wake region and the surrounding area around the models to sufficiently capture turbulence and flow separation. Yes, this is what I mentioned a while ago. It's very important you capture like the transition, like the turbulence and the flow separation. Yes, because like your end value will be very like the value will be very different because the values are like affect each other, right? This is done to ensure the computational fluid processing is focused on more important regions in the flow regime while keeping the far field sufficiently coarse enough as to not dramatically hamper computational time. Hey, the overall grid is limited to a maximum spacing of 0.1 meters in a minimum of 2 mm. Good enough. The smaller, finer VOI sized by the bounds. Okay, these are the bounds. I don't want to read all of these. In a larger, coarser bodies of influence is defined by all in meters. Lurk for a bit. Thank you. Thank you for the lurk. Larger, coarser boy. A conversion algorithm in Fluent was used to convert the preliminary tetrahedral and prismatic grid into a polyhedral one. Polyhedral exhibit advantages over tetrahedra, namely, they approximate gradients better than tetrahedra due to the fact that they are bounded by many neighbors. Additionally, polyhedra have a more lax geometric criteria due to their insensitivity to stretching, making grid pre- and post-processing easier. This is well suited to highly complex geometry of the models used. Yeah, I think I mentioned a while ago that the meshing per program, like they can have different shapes, like so that's basically like the shapes of the grid. They mentioned like insensitivity to stretching, so I'm not sure what they're talking about, but like in like some meshing systems, if you stretch your grid too much, it will diverge. Like it has there's like a recommended aspect ratio of the elements in your grid. Like for example, if like this side of this one grid element is way larger than this other side, like it's like low quality, and it's like it can cause cause your simulation to diverge. So yes, it's very important. Like the grid is like super important in ensuring not only the accuracy and capturing the changes, but also making sure that your simulation actually solves and doesn't, go to infinity. Trust me, I'm an anime girl with glasses. Thinking of how you'd program physical simulations. What do you mean, like stresses and stuff? I think like it's not really that. I think like there's like an auto like mesh grid in the ones built into cats especially. It's not that painful. If you're lazy, you click the auto. just press the auto. All the software have the auto. The different stages of Shinobu would have been perfect for this paper. Missed opportunity. You're so right. I like how your brain works. A 2D girl teaching about 3D models. Can we really trust her? Not from scratch like any true computer. Held a message for reason disability. I'm so sorry about Automod. I'm sorry. It said you got held for disability. Rura, you're so bad. You should be nice to the disabled people. I need to pin this message. This is so smart. Yes. Automod hates me for being It has been observed that polyhedral grids provide the same level of accuracy as tetrahedral ones, but of significantly lower element count, thereby hastening simulations. Furthermore, polyhedral grids have shown to improve convergence while having notably greater accuracy under unsteady simulations. This is further supported by similar external aerodynamic studies run under Fluent, where speed-ups between 2 to 3 times towards a converged solution have been observed. Enter the digital focus. They also only did aerodynamics. What about durability? Yes, we need fatigue analysis on anime Breast. Yes, we need a fatigue analysis. We need repeated stress. We need the cycling by my fist, by punching and not punching. Yes, repeated punching. Hey, stop making me say things. Hey, you're gonna. I'm. Sorry, that wasn't me. I'm sorry. I'm an anime science girl. I don't like punching women. I like women. I treat them respectfully. First job. She directly went to the. What am I supposed to think? If you think durability isn't like the number one test for. Thank you for the follow, Relialec. Thank you. Isn't when you think of durability, isn't the one of the most standard mechanical stress tests you do, like fatigue, testing for fatigue by repeated cycling of stresses, aside from like a drop test also for like the maximum stress, aside from like the cycling stresses. See, I can do that. I can do that. Trust me, I know mechanical testing. Trust me, I'm a mechanical tester. If you speak, you're in big trouble. Because we're on a perpetrator. Sheer test. Sheer test. Oh God, please. What is happening? Shear test. Stretch. Turbulence model and computational approach. The flow around models is modeled with Reynolds average Navier-Stokes equations in incompressible form. What do you mean incompressible flow? Written in Cartesian tensor form and having flow variables of the form. What do you mean? What do you mean incompressible? What? Being substituted into the instantaneous continuity and momentum equations of the exact Navier-Stokes equation, we obtain this equations, this Navier-Stokes equations, they're also included in the test later. Make sure to memorize them. The closure of the set of equations are done by means of Mentor's two-equation blended K epsilon and K omega shear stress transport model. Yes, the SST model, which computes eddy viscosity with a linear stress-strain closure. Mentor's model combines and smoothly blends the individual strengths of the K epsilon and K omega models, where the K epsilon sufficiently predicts turbulence in both the free stream and wake, and the K omega model more accurately prescribes boundary layer separation in adverse pressure gradients near no-slip surfaces. You're failed physics students. You left equations behind me in the uni. Oh, don't worry, now's your chance. You've been given a second chance. The exams I will give you, it's your second chance. Yes, you just have to memorize the Navier-Stokes equations and the drag coefficient equations and the Reynolds calculations, both for the turbulent ones too. Yes. The spatial convective terms in equations 9 and 10 are discretized using second-order upwind scheme, except for pressure being solved using Breast, pressure staggering option, which is similar to staggered grid schemes used on structured grids. With the diffusive terms discretized using a weighted least square cell space construction technique. The inadequacies of the least squares approach are well known. However, it provides accuracy that is comparable to nodal schemes, and due to the use of a polyhedral mesh, the least squares approach provides an adequate balance between computational expense and accuracy. Presto with an exclamation mark is one of my favorite shortenings. Yes, they didn't need the exclamation mark, but they put it there. You did pass physics, but you don't remember any of it. I thought there was software that would solve these things for us. I mean, these are yes, but before you're worthy of the software, you have to pass the exam first. You know, it's like, before you're worthy of it, I mean, I already passed it. I don't need to know any of this crap, but you do. You need to... I am the streamer, you are the students, and thus I don't need to take the exam, only you. Yes. Simulating the flow around the human body was found to be naturally unsteady, as shown by Edge, and the ideal approach would be solving the flow equations in a time-dependent fashion, then finding the computed mean quantities manually. Yeah, so this is actually very computationally intensive. If you make like simulations that's like transient. It's like transient simulations are the simulations where like there's time and then per point in time you solve. So remember how like there's a grid, there's like a mesh here, right? There's a mesh where you solve more, the more detailed the flow is at this anime girl Lukoa. If you do transient simulations, there's a similar time grid wherein you have to focus like the solving at the points in time where it will change the most. Although here the input is just steady, so I think it doesn't apply to that you need to make like a grid, a time grid. That's complicated, but still, you should download Mathematica. Why Mathematica? You should use Mathematica a lot in a bunch of your courses. No, MathCAD is superior. MathCAD is superior. Downloading your ex. Saying I should download, it's like saying I should call her if you think about it. Oh my god, where were we? Oh, we were at the part about transient. Simulating flows in a time-accurate manner and finding the computed means would be prohibitively time-consuming for the study, especially since there are a total of 18 different runs. What? This guy has a weak-ass computer. Just 18? Just 18 divisions for your transient simulations, and it's too much for you. In addition to this, obtaining time average results from transient simulations for all of the required runs would require computational resources beyond the capabilities of the author's reach. What a loser. That's right. Yeah, so what happens in transient simulations is, since you're simulating at different points of time, basically per point in time you have to solve again, right? You need to have results per point in time. So for example, for 1 second you have to, before you simulate 1 second, you have to simulate the starting first of all. And for example, you get it you make a simulation 1 second, it has to converge first, right? And then you have to make another run for 2 seconds, for example, and it has to converge all over again. But usually it doesn't take as long as the first run, because when you have the results for the first run, you can initialize at that value so that you're not starting from scratch. You're not solving totally from scratch. You can use the ending values in order to initialize the next step of the simulation, if that makes sense. But yes, what a loser. Thus the most realistic and only feasible approach was to attempt steady state calculation. No, we won't get a fancy video, because if you do a transient simulation, you can have a cool animation. You can see a cool video animation of how it changes per second in time. You get a cool ass video. Don't you want a cool ass video? Hi Vivi, welcome. So yes, this author, using a steady state calculation instead of a transient simulation, this author is depriving us of a cool ass video. What? You do like cool ass videos? But yeah, steady state simulations is actually the first step. Anyway, when you do transient, you have to make sure it's gonna converge at steady state first before you try to put it at transient. This guy was only using 4 gig of RAM. Be kind. No, I'm judging this guy. I'm judging this guy's steady non-transient simulation. Look, I'm gonna judge this guy's grid, computational fluid dynamic grid. Look at it. Look at that. Look at it. It's so square. It's not. They didn't even shape it. Look at his weak ass computer. If this was, look at him. He put like the concentration of the mesh here when he could make this concentrated everywhere. If his computer was strong enough, like the stronger your computer, the lazier you can be at computational fluid dynamics. Basically, because if not even using H100, because like basically the lazier you are, I mean the crappier your computer is, the more work you have to put in computational fluid dynamics, because you have to optimize, because you have very limited computer resources, so you have to optimize your mesh. You have to like optimize your solving settings, your initial values. Whereas if you have a strong computer, you don't really need to do this. Just make everything strong. Just waste your computational resources. Who cares? Your computer can handle it. Yes. Oh no. Well, trust me, I'm a pro. Trust me, I'm a pro fluid dynamics expert. So what's the scientific conclusion? Oh my god, we're not even halfway. I'm so sorry. You can read the end of the paper if you want the conclusion. Yes, sorry, I keep getting distracted by my tangents on computational fluid dynamics. I'm so sorry. The computational fluid dynamics code, let's see, where were we? She is responsible for melted components her advice causes. Hey, what do you mean, Hey, so this... No, what are you gonna say? What are you gonna tell your boss? I'm sorry, boss, I listened to this anime Opabinya girl on Twitch tell me how to do my meshing for my thermofluid dynamic analysis of your device. Like, I'm sorry that yes, it exploded. Yes, it wasn't me. It wasn't me. You have a diagnosis for... Sorry, it's hard to read some of the chats. Like, this calculus, so watching this is an experience. Like, some of the words are like being covered by like the pin icon. I don't know why. I'll probably let Vinny tell you which two are real, and then you would tell your boss. She did say to trust her. Yeah, where are we going? I was getting disappointed at this guy for doing a steady state flow instead of transient simulation. This method is not without major drawbacks. Notably, obtaining exact quantities can only be achieved by finding the limit of an infinite sample, and it is therefore expected that the computed mean will contain sampling errors. Moreover, this approach would more than likely imply that small shedding features are not resolved and thus their effects on the overall flow are ignored. This suggests that there will be accuracy implications in terms of solutions to the problems under examination. In order to give the simulations a semblance of a fighting chance, would never steer me wrong. Yes, trust me until you get in trouble, then sure, blame me. Let's see. Like, just try and blame me. See what happens. A pseudo-transient time-stepping method was applied to the flow equations being solved. What? The implicit under relaxation serves as predictor corrector method with the objective of fast convergence and accurate temporal integration that achieves an approximate steady state. Furthermore, the use of pseudo-transient under-relaxation factors was found to accelerate convergence in a more robust manner, and the rate of convergence has been shown to reassuringly arrive at a solution earlier than without the use of these under-relaxation factors. Hence, by taking advantage of the natural structure of the problem, by evolving flow equations in time, we were able to achieve a solution that reasonably integrates transient effects in a way that can be realized through the use of a steady-state calculation. In Fluent, the pseudo-time step was left to be calculated automatically, following the recipe found in the theory guide. This was done to hasten setup and retain consistency across all 18 simulations. Drag coefficient versus the number of iterations on a medium mesh with an inlet velocity of 10 meters per second. So these are, you can see here. So this is usually what you can see this file vignette. Yes, I am follow. Yes, you will follow everything I say now. Give me 100 subs right now. I don't often drop my phone on my face. At least it was there to wake you up. Very smart. So you can see here there's an iteration versus drag coefficient graph. So yes, basically the number of iterations, it's like when you simulate, it's like an iterative sequence, right? So usually like the way it's solved is usually you'll see your values becoming more steady the more iterations there are, supposedly. Good night. Good night, Kataru. Sleep well. Thank you so much for stopping by. This hot button only makes me fall. I don't even know where the sub button is. Convergence discussion. Thank you for stopping by. Thank you. I'm sorry you didn't even see the result because I keep going on tangents about CFD. I'm sorry. I will do more reading, less tangents about simulations. Initial calculations were run to preview the exact behavior of the iterative calculation process. Indeed, as previously demonstrated by Edge et al. Big spoilers. The inherent unsteadiness of the flow resulted in difficulties obtaining reduced residuals. Yeah, so residuals are like, that's usually how you set your that's usually like the convergence. Oh no, I'm going on a tangent again. But yeah, usually like the solving criteria you set in CFD software, you set like a residuals that is your target, that if it's like reaches this residual, then it's gonna stop solving and it's gonna call your solution as solved. So it's a value that's like, it's up to the situation. Like it depends on how much accuracy you are looking for. It also depends on like what you're solving for. Like sometimes something will solve forever because you set your residual too high. So it's like basically how strict you want the program to be solving, and how heretical would be if it went opera. What? Why would you do such thing? No, I hate how that works. I hate how that's like a clever name thing. Well, yeah, so they're when they're talking about the unsteadiness of flow in obtaining reduced residuals, it's like you need the residuals to be reduced for it to, you know, consider solve. So yes, with a scaled continuity, residuals hovering below but near 1 to 10 to the negative 2, and other residuals remaining below 1 to 10 to negative 4. So a technique stemming from experience was devised to assist in reducing the residuals while maintaining spatial accuracy. For the first 50 iterations, a blending method between the first and second order spatial discretization schemes with a bias for the first order scheme, lower URFs, and an aggressive pseudo time step were used to rapidly approach a quasi-stable solution. Following 100 iterations, switch the spatial discretization scheme to a higher order method along with raised URFs to increase accuracy. The remaining iterations were then run using a conservative pseudo time step scaled by 0.5 to further converge and resolve flow details and that are more apparent on a smaller time scale. This technique enabled the residuals to drop by nearly an order of magnitude, and thus it was used for all other simulations. My brain is too small for the stuff your biology cell compared to physics jazz. No, don't worry, I don't know what. We'll hold it flat, maybe just as we can't be sure if it's okay. Wasn't that a toggle actually? Fine, you really want it. Fine, you really want it. You know what? Fine. Fine, I can't believe you. I can't believe you'd make me do this. I can't believe you'd make me do something like this, but fine. I can't believe you make me. I can't believe you make me do something like this. It's not. I even have to do this manually. Like, a transform attachment attached to character 1, attach type human body bone, attached to bone chest, and then we have to get the source, the core source for the 3D file, which is this one, and then oh my god, that's too big. That's too big. Hold on, too big. They're too big. That was the default size. There are you happy now? Are you happy now? Are you happy now? I hope you're happy now. I hope you're happy now. Yeah. Is this what you wanted? Is this what you wanted from me? Is this what you wanted? I should totally not click that. Fascinating. God, you're paying so much attention to this class now. Thank you. What do you mean you weren't paying attention to me a while ago? What I was telling you about, I was explaining this paragraph to you. Do you understand this paragraph on your own? Now do you even know? You didn't listen. Would you have known what this meant? Huh? You're still looking at the words. Sorry. I can't believe you guys will do this to me. Look, fine. What does this paragraph mean, huh? Huh? Did anyone listen? Huh? Are you looking at something else? big round glasses. Looking. Oh, at that, I remember your shitpost drawing of Kai. Like, it's still on my mind. Your shitpost drawing of Kai is still on my mind. Okay, is currently iterating over something already. No. But yeah, so basically what this paragraph, Kai guinea pig man Nikki, the guy drawing his pig. I don't know. But yeah, so basically this guy has, I think he has a crappy computer, so he has to resort to desperate methods in order to get his simulations to converge. So, like, ideally you set your solving settings, right? You set your solving settings and then you press solve and then it solves, right? But no, so it doesn't solve. So what he does is, when the residuals are still really high, in order to get them down, he makes the settings like a lot more aggressive. So yes, so, and then basically you just, like, at different steps, like depending on how solved your equation is, you become more or less, you can become more or less aggressive with the solving. Like, example here, he lowered the relaxation factors, because like the relaxation factors have a really huge effect on the speed. It looks like they're resting on the bottom of the screen. It reminds me that I still need to do something with the fact that Kai and Ace be on identical elephant garments. But that's what would you do with that? You would join them. Of course, that's what you would be doing. As discussed in section 3.3, taking mean quantities of a finite sample will incur sampling errors, of which are difficult to quantify compared to a mean derived from an infinite sample. However, a potential approach to help determine the exact nature of these errors would... You're listening to me because of this, right? You're concentrate because of this, right? It has physics. It has physics. See? Has physics. Stop imagining the physics. However, a potential approach to help determine the exact nature of these errors would be taken as an integrated surface quantity, such as drag coefficient, and seeing how this quantity changes as the iterations progress. Such a measure serves as an observed global variable in that measured quantity is dependent on how accurate the grid can resolve the flow. Figure 6 shows the iteration history of drag coefficient between the two models, taken with an inlet velocity of 10 meters per second, and then run using a grid with medium refinement. The figure shows that the solution reaches quasi-steady state values after 150 iterations, with an oscillatory period occurring roughly every 140 to 150 iterations. A 100 iteration moving average calculated by Fluent was applied to the values to assist in determining if overall convergence was reached. Looking at the tendency of the averages, it is reasonable to conclude that the solution is indeed quasi-stable, with the average varying very little compared to actual iteration values. And for the sake of minimizing computational expense in this study, this observed tendency incurs a reasonable assurance that the simulations are adequately converged. Finally, the net flux imbalance was calculated to be less than 1% of the smallest flux through the domain, further supporting convergence. So yeah, if you're like a solution doesn't completely converge in like the settings you set, like the residuals, you can make a personal judgment and see if it doesn't seem like it's changing significantly anymore. You could just like, oh yeah, that's converge. Yeah, that's converge. That's done. I'm done. I'm done. Yes. But like that's like very dependent. I feel like that's very dependent on on the person doing the simulations as well. Moving forward, to preserve accuracy and to assure low computational costs, the effect of grid resolution is studied by comparing results on drag coefficient using different grids of different refinement. Oh my god, it's been 2.5 hours already. I'm so sorry. Why are you still here? It's been 2.5 hours already of me reading fluid dynamics. Like, don't you just want to look at the pretty pictures? Like, look at the pictures. It's our entrailment. What a marathon streamer. I mean, learning. Oh god. Oh god. Oh god, I thought I could read. Okay, I can. I'm gonna stop. I'm gonna stop tangenting. I'm gonna stop. Like, the reason I keep tangenting is mainly because I keep judging this guy. I will stop judging this guy. You have to know if flat is truly just. I'm gonna stop tangenting and then stop judging these poor guys. Stop. It's because you're so, oh my god, I'm so smart. Yes, tell me I'm smart. Yes, praise me, give me praises. Like, aside from smart, what else am I? Yes, I like praises. I do like praises. I trust you to deliver now. Moving forward, to preserve accuracy and to assure low computational cost, the effect of grid resolution is studied by comparing results on drag efficient using different grids of different refinement. The importance of grid convergence and examination of discretization errors in CFD simulations have been demonstrated across numerous organizations and journals, and the necessity of quantifying these efforts have led to well-established methods that attempt to describe effects of resolution to that of the extrapolated solution. Although it has been repeated in this paper that quantifying exact errors is essentially a fruitless adventure, the additional time spent on understanding the potential discretization error nonetheless is useful in helping select the gridded balances, the required resolution, and minimal processing power. You're happy? I'm seven. Stop the slander. Very cute and smart, and both in a superposition of being flat and buoyant at the same time. Quant method. You're saying she's dense? I'm dense in neurons. I have lots of neurons. That's what you mean, right? You created another Alfred record. Oh no. Oh no. Oh no. Let's wait. I gotta. Did you? Oh no. Oh no. click on the link, please. Please click on the Twitter link. Please click on it. Oh my god. It's like when you're perceived. Hey! You're saying I'm so. You have hands in bikini. Oh my gosh. I like how there's eyelashes. It's like you can't even lie flat on the ground because you have to. You can't even lie flat on the ground because it's too massive. It's too massive to even lie down. It's like, oh no. You have the power of creation in your music. No. Oh my god. This looks like it looks like balls. I'm sorry. Thank you. Thank you for the. Thank you for the. Thank you for the. I don't know how to call this art. Thank you for the artistic rendition. Thank you for the anatomically accurate rendition of Pabinia regalis with the anatomically accurate cup size. No, baby, no. Why did you? Baby, no. Why do you have to say it like that? No. Oh my god, I'm gonna. This paper's already killing me. Now you guys have to kill me too. No, the C for the proposes, please, no. Please, no. Please, no. Please, no. No, what is this chat? What is this chat? What did I do to deserve to cultivate a chat like this? Please no. Please. I'm gonna put science in your brain. Yes, you need more science in your brain. You've been grown with you. In this grid refinement study, each model used 3 different grids that are refined methodologically by decreasing the cell spacing within the BOIs. Between both models, the grid generation method remained the same and follows procedures as described in section 3.2. Representing fine grid, medium grid, and coarse grid. Oh my god, my accent is coming out. I'm sorry. The normal model utilized grids containing 2.82 times 10 to the 6, 2.32 times 10 to the 6, and 1.53 times 10 to the 6. Delirious because no sleep. You can, but you're always... You guys are always sleep deprived. Oh. Are you petting me? The difference in overall element counts are attributed to the reduced surface area of the flat model compared to the normal one. Yes, you need more element counts to capture the curvaceousness, yes. For the sake of completeness and following the method as recommended by the American Society of Mechanical Engineers. The subsequent equations are presented to determine the discretization error between the described meshes, letting H denote the representative grid size. Yes, you need to memorize this equation too, where delta V sub I is the volume of each cell, and let H sub 1 less than H sub 2 less than H sub 3, and let R designate the refinement ratio between successive grids such that R sub 21 equals H sub 2 over H sub 1. Yes, you like listening to this. And R sub 32 equals H sub 3 over H sub 2. Yes. How fun, how interesting. So interesting. Cube root of a delta volume sum is calculating the apparent order of accuracy. Okay, fine, we can skip. It's actually not that important. It's actually not that important, so this part is just basically just a grid refinement study. So it says, so a grid refinement study is basically where you do a couple of runs with different grid refinements. I mean, and then you try to see where it matters, because like there's diminishing returns, right? Like of course it's more accurate the finer your grid is, but like there comes a point where it doesn't really matter anymore, when it's like past a certain point and the values stop changing in the significant values that you want. So it's basically like, if you want to be efficient, grid refinement study helps you know like how much, at what point is like the trade-off worth it for how fine the grid is, and the computational resource it takes. So that's basically just this. It's like just a grid selection. That's how I understand it. I mean, I could be wrong, but that's like how I understand this. Yes. The headpad could crush her whole body. If not, please understand, I'm a soft-bodied Cambrian creature. I'm soft-bodied. My prey is soft-bodied too because I have no teeth. Okay, results and discussion. Yes, the moment we've been waiting for. The immediate discrepancies between Lukova's model and other human models used in similar studies, other than the fact, oh my god, what is this? Look at this sentence. Look at this. The immediate discrepancies between Lukova's model and other human models, other than the fact that she has an enormous chest. Look at this study. look at this wording. Look at this wording. This guy, or the presence of horns, a basal cap, raised arms, and solidly modeled. What is this? What do you have to say it? Do you have to say it? He's got. I mean, it is enormous. It's actually objectively correct. But this guy, you know what's, I'm so impressed at how much this guy has managed to include in this paper. Like, I'm in awe at how much shit he's managed to sneak into, like these sneaky statements. Like he's been like trolling us in so many of these paragraphs. It's important to recognize that although these differences between Lukoa and other human models are present, they nonetheless do not affect the direct comparison between the normal and flat models, which was a primary objective of this work. The following subsection details the variances of drag and lift as air velocity changes. and compares the outcomes to previous studies on the human form. The subsequent subsections delve into the differences in wake structure through the analysis of streamlines, velocities, TK, and skin friction. While no sound comments can be made on the concise form of instantaneous flow structures, quasi-steady-state general features present in the flow are described. The convergence method present in section 3.4 was used for all velocities listed in Table 1 between the two models. The drag and lift were calculated using the same 100 iteration moving average and fluent, and the values at the end of 400 iterations were used. Figure 7 to 9 plots the results between the two models. In all of the figures, a cubic spline was used to interpolate data. The figures labeled with A correspond to drag-related values, while the figures labeled with B correspond to lift-related values. Oh, we're at the graphs now. Skin friction. Okay, so here we see LUCOA, normal, and flat. So, per air velocity. So we can see here that the flat one, fitted curve, has a higher drag coefficient than LUCOA normal. And we can see that the LUCOA flat has a higher lift coefficient than the LUCOA normal. Not looking good flat and drawers. So much lift. The drag force versus air velocity. So in all graphs we can see that for all values the flat LUCOA has higher values. Relative drag difference of the flat to the normal model. This is for air velocity. Figure 7 focuses on the coefficients, and it is readily apparent that at all velocities the flat model incurs higher coefficients than the normal model. In the region near 5 meters per second, the drag coefficients between the two models were closest to one another. Judging from errors described in 3.5, it is safe to presume that these differences within the error bounds and therefore negligible. In 7a, this is 8, it's the drag coefficient. It's interesting to observe that the drag coefficients decrease following a power relation corresponding to a velocity. This relation most likely arises from the peculiarity of solidly modeled hair. Downwash due to the hair diverts air behind the torso, then directs hair downwards, which causes less air to flow directly behind the body. Yes, there's like a wall behind. Presumably, this downwash closes off the size of primary recirculation region behind the body. Two big old plain noses right front. Honestly, I guess it makes sense if you're modeling booba solids, because at that point they're wind reflectors. As the air velocity, yes, yes, trust me, I have seen a real woman. And at air velocities of 30 meters per second, it stays rock solid still. Yes, at high wind speeds, it doesn't move. Yes, trust me, I know how women look like. Yes. As the air velocity increases, the effect of the downwash becomes more prominent, and therefore a general decrease in the drag coefficient is observed. The large breasts on the normal mode may also play a role in enhancing this downwash effect, as the air is gradually diverted around the bust and is able to maintain momentum before being redirected by the hair, the stronger resulting downward jet of air thus closes off the recirculation region more effectively. The degree of which this downwash affects drag is difficult to determine from this study, but it is reasonable to deduce that due to the drag reduction of the normal model compared to the flat model, the effects are markedly noticeable. The geometrical presence of the breasts may also have an effect in reducing drag as they smoothly redirect a portion of the air around the torso, whereas the flat model simply forces the majority of the air to stagnate at the chest, which incurs higher drag. No, the geometrical presence of breasts reducing as they smoothly redirect a portion of air around the the flat model forces majority of air to stagnate at the chest. No, it's like it just hit a wall. It's like it just hit a brick wall, and it just hit a wall. No. What do you mean? The air just stagnates at the the flat chest? Oh no. The difference in lifts is notably more dramatic than drag. In figure 7, the lift coefficient for both models gradually increases from 1 to 10 meters per second and levels off as the velocity changes. This increase can also be contributed to the downwash from the hair, since as the velocity increases, there is a higher flow rate and thus more fluid mass pushing upwards against the models. The brim of the baseball cap on both models may additionally contribute to lift as it lies orthogonal to the mean flow direction and causes a buildup in pressure in front of the face. The normal model provides a lower lift coefficient, possibly due to the breasts providing downforce, since the normal model has a significant and primarily upward sloping surface in front of the torso that the flat model lacks. The downward force from the air flowing atop the bus most likely provides this reduction in lift. Granted, due to the geometry being modeled as completely solid, this effect does not account for breast deflection caused by these forces. Breast deflection. Nonetheless, the presence of Lakoa's large breasts evidently provides a reduction in lift. No. Presence of Lakoa. Yeah. Like they could word it, like they could just word it, the presence of they have to say Lakoa's large breasts. Yes. Figure 8 provides a comparison of the actual forces experienced on the models, as seen in both A and B. Yes. The forces increase following a roughly squared relation, which is what would be expected looking at the velocity relationship in equations 1 and 5. As elaborated in the previous paragraphs, the difference in drag is less dramatic than that of lift, and this is reflected by the more difficult to discern plots in A than B. This observation is further expanded upon in figure 9, which compares the relative force difference the flat model encounters compared to the normal model. Looking at 9, the flat model experiences a nearly 4% increase in drag at 1 meters per second. However, this value decreases immediately and falls to below 1% at 5 meters per second from 5 to 10 meters per second. The difference between the two models widens again. Whoops, sorry, this is the other paper. This was the Anomalocaris. I think this was the Anomalocaris eyes. Yes, this was the Anomalocaris eyes. I still have it open. The reason as to why drag difference reaches its minima at 5 meters per second cannot be directly inferred from this work. Throughout the tested velocity range, the flat model incurs an average drag increase of 2%, which in the context of day-to-day life at low air velocities is practically insignificant. However, in regards to performance, the large breasts on normal model can prove to be advantageous, assuming the overall position remains similar to the erect postures of the models. The degree of which this advantage can be quantified depends heavily on the type and duration of competition to be examined, which is not discussed further in detail. Yes, the relative lift force difference averages 24%, with the values ranging from 32% at 1 meters per second, gradually decreasing to 21% near 15 meters per second, and slightly increasing to 23% at the highest test velocity. Aerodynamic analysis of anomalous cars. The computer I'm using will die. But yeah, there's actually Anomalocaris models out there. Like, there's this really amazing Japanese modeler who makes like VR chat MMD models of Cambrian creatures, and they have one of the Anomalocaris. Yes. From this result, the presumed effect of Lukova's breasts reducing lift is more pronounced at lower air velocities, while still remaining effective as the velocity increases. Like, I like how they don't even say larger breasts. They have to say it's Lukova's breasts. Comparisons of drag coefficient with other researchers' results. Yes, they look like they're within the range. Table 3. Pulling up VR chat how that's Anomalocaris smoking. Yeah, there's a free Opabinia VR chat model as well. Like I can be the Opabinia, I can be the... No wait, the Anomalocaris will prey on an Opabinia. Well, to be fair, who else but Lukova could have size S boobs? Yes, that's right. Table 3 summarizes the encountered drag that both models experienced throughout the tested velocity range, together with other researchers' experiments. Hi, Agumi. Thank you for a follow. Hi, we are currently... Yes, we are... Yes. Aerodynamics of breasts. Opabinia or Opai paper. Large rock solid breast. As a result, the present study reveals that Lukova's form tends to correspond favorably to experiments done with standing models. It is seen that Lukova's results overlap with those of Hill and Brownlee et al. Schmidt's results were an atypical case, as the drag coefficients in that study were based on the entire surface area of the body divided by the product of volume and subject height instead of the customary frontal projected area used elsewhere. This resulted in coefficients ranging from 10 to 13, necessitating a recalculation in order to more directly compare to the other results in Table 3. It was demonstrated through Schmidt's results that the use of nude subjects, akin to having smooth walls as mentioned in section 3.1, result in lower drag. Yes, yes, if you want if you're doing something that needs aerodynamics, like skiing, just be nude. Yes, just be nude to the tourist. I don't know what I'm saying anymore. Although the values for nude subjects were still greater than those found in the current study, this finding provides additional support as to why Lukova's overall form tends to encounter lower coefficients in contrast to other studies. With the objective of obtaining C sub D values, coefficient of drag values for a wide range of people in everyday situations, work done by Penn Warden confirms that clothing certainly increases drag. Furthermore, the authors in the study comment that extrapolating their data to simulate bearskin models would result in values more akin to that of Hill's data, therefore supporting the notion that Lukova's results are indeed realistic. And get next time you need to run your store. Yes, thank you for using science to make your everyday life easier. Parachute jump nude preventions of breaking the self-barrier. Yes, apply. Science is useless if you don't apply it. So yes, apply it. Comparison to results based around running are also provided, as this form of competition is a natural progression from simply standing. Understandably, a runner will experience a higher drag due to their ever-changing position and the strict anti-symmetry in orientation. Shane Brook and Jazz Kazak, I don't know how to pronounce that. I don't know what language that is. Investigated drag through the use of a generalized cylindrical human model, analogous to the assumptions described in section 11. Yes, you are a can. As such, the results parallel those of other investigations done on runners and show that a cylindrical model can provide convincing data. Davis' work discovered that the effects of Reynolds number remain constant below velocities of approximately 18 meters per second. Conversely, this effect was not seen in this study, which most likely harkens back to the drawback of the modeled hair. Gomez et al. Developed a parametric model of drag that considered both velocity and acceleration based on the record-setting performance of Usain Bolt. They revealed that 92% of energy used in running is absorbed by drag, which bolsters both the significance of the drag reduction and implicational anthropomorphic advantage that Lukova has. See? Polish name spotted. I wouldn't know. I have no idea about. Yes, I'm too Asian. Yes. So, oh my god, look at this. Look at this. Look at this. They're talking about Usain Bolt, and then they said the advantage that Lukova has. So Lukova has a more advantages for him than Usain Bolt for Olympics. I don't know what they're trying to say. I don't know what they're trying to say anymore. You do your best to learn about other cultures more accurately. Anyway, Lukova could absolutely Usain Bolt in the Yes, I think that's what they're trying to say. What they're saying is Usain Bolt needs a massive rack. Oh my god, stop it. What are the mental images? Just the cursed mental images. Where's cursed mental images? I can't. Consequent. That's the word we. Inu et al. Examined the effects of a moving belt system to simulate ground effects of a runner. in addition to providing data on how leg position changes drag. From their study, it was observed that having the legs placed either forward and behind veritably increases drag due to the posture. Consequently, it is expected that the prospective study incorporating the effects of running based on the present results would feature comparable C sub d values. While the current stationary results may not be directly applicable to the moving case, they nevertheless offer a suitable starting point on which to base further research. The same poop. Salient flow analysis discussion. Oh my god, why are you guys still here? It's been 3 hours. Discussion pertaining to the variances in flow structures is examined under an air velocity of 10 meters per second, in addition to being previously examined in sections 3.4 and 3.5. This velocity is readily available under human locomotion, making the selection straightforward. While the results are derived from a quasi-steady-state approach, general flow structures can be reasonably interpreted. We're getting look like I'm doing this because I want to read this paper, and then I'm like, why not hit 2 birds at 1 stone? Why not make it a stream so you're like doing something I was going to do anyway, but also streaming. Like, I'm doing this for myself. You don't have to sit through 3 hours of me reading a science paper. I would like imagine someone asks you, how are you spending your precious weekend time, your precious time off work, and you're like watching an anime girl read a scientific paper for 3 hours? Is that what you're gonna say? You're here in search of inspiration. You found it. Yes, your art was certainly inspired. Cute girl. Nakoa is cute, yes. As reflected in figures 10 to 13, the fluid dynamics of the wake are shown with the use of streamlines colored according to velocity magnitude. Figures labeled as A and B correspond to the normal and flat models respectively. I don't think you need to label them. I think we can see which model is flat. The overall wake structures revealed in figure 10 fall into 2 distinct regions based on height, with a PRR found above the hips extending to the top of the head. Above the hips extend, yes. So I think PRR is you can see like what the section they're referring to is where you can see the recirculation happening. The work described in section 1.1 correctly predicted these structures, specifically the PRR for both models was found to extend roughly 1.4 meters downstream, or approximately 4 times the width of the torso, which agrees strongly with Okamoto and Tsunabashiri's findings. The type of vortex shedding in this recirculation region cannot be determined, but it is expected to nonetheless be asymmetric, with the large-scale structures being advected downstream based on the findings of Edge et al. Okay, it's time to look at images. Wake structures. So what can we compare? Yes, here you can see from the streamlines, you can see the smooth line here. Can you even? And then here we can see the yes. I'm about to go back to bed. Thanks for teaching me about robophysics, and you're welcome. I hope you passed the exam that you have to take as soon as you wake up. Have a good night. Thank you so much for staying so long. listening to me read a science paper. Good night. It's like an F1 car. Yeah, it's like an F1. Set of vertically aligned streamlines on the normal model. Set of vertically aligned streamlines on the... Oh no. You can see the streamlines. You can see the stream. You can see it. It's like hitting a wall. Oh no. Look at it. It's like... Oh no. No, this cannot be. This cannot be. I think this study is it's so biased. It's so biased against flat. Like if they rotated this 90 degrees, then look what would have, then the big breast would like block. They just have to make it sideways. They just have to like they have to put like the inlet. They should have put the inlet of the air, the inlet of the flow perpendicular like this. Oh my god, no, sorry, science is broken. No, it was biased from the beginning and was a setup. Instead of like putting the inlet this way, they put it this way. This cannot be. No, this cannot be. This cannot be happening. On normal model above the bust. What's this? Why does it look like it's smoothly curving upwards, and here it's like... No, this cannot be. No, it's just the boundary conditions. It's just the way they set up the simulation. They were biased. No, this cannot be. Hi, between boundary. Hi, we're currently studying the we're currently studying the computational fluid dynamics analysis on anime breasts. Yes, so because aerodynamics is very important for sports, because yes, it's very important because they studied in the Olympics in Usain Bolt. Here they said that 92% of energy used in running is lost because of drag. That's why if you're gonna participate in the Olympics, you study it in your free time. Then I think you're gonna pass the test. Yes, that's why in order to reduce the 92% of effort that's being wasted on drag, you have to have the most aerodynamic form when you're participating in the Olympics. Yes. Oh, thank you so much for the follow. So far we've found that there's higher drag on the flat chest because, as you can see, the streamlines are just hitting a wall, which I think is like injustice. Is absolute. This, no, I don't accept this. It's because they put the airflow this way, like from the front. That's why this has a more gentle curve. But imagine if they put the airflow from the side. If they put the airflow from the side, then this would have more resistance, because there's like a boob here, but here there's less resistance because it'll just pass through. So I think the author is very biased against flat is justice. Flat is justice. It's just that justice is extreme. Hey, airflow as if they shot out of a gun. The type of vortex shedding in this recirculation region cannot be determined, but it is expected to nonetheless be asymmetric, with the large-scale structures being affected downstream based on the findings of Edge et al. The wake behavior behind the legs were also discovered to obey the findings summarized by Tu and Alam, with the region from the ankles to the knees having wake structures associated with each leg, and the region from the knees to the hips behaving as a unified bluff body. The figure also shows a distinct vertical jet sheet stemming from the gap between the legs with an average magnitude of approximately 35% greater than the free stream velocity. Wait, where's the thing from the side gap? Where's the pictures? A vortex pair originating from the top of the legs is also evident. The vortex pair can be seen being caused by the downwash of the hair. The momentum of downward flow interacts with the air flowing past the top of the thighs, which results in these prominent structures. You know, you could just pretend that Lukowa uses lots of hair gel. Like, where did it say that Lukowa didn't sometimes use so much hair gel that it became rock hard? Yes. Still, it's possible in real life. From what can be drawn from comparing figure 10, A and B, the flat model has a weaker, less organized vortex stemming from the legs. This observation may further explain why the normal model has a lower lift than the flat model. What if she wants to fly? Eider et al. Described the effect of the vortex pairs affecting lift and drag, and shown that the inflow caused by the streamwise counter-rotating vortices result in a net downward force. Thus, the weaker vortex pair on the flat model contributes less towards reducing lift than the normal model. Following this, it is reasonable to suggest that the behavior of the drag curve in figure 7 can be attributed to the formation of these vortices. The energy being redirected into the formation of these structures diverts a portion of the mean flow away from the PRR, leading to the drag reduction as velocity increases. Figure 11 provides a close-up look at the same streamlines in figure 10. Yes, I saw it. Yes, it's painful to look at. It's like hitting a wall. Look at this, it's like hitting a wall. The pain. The breasts provide a gradual interface for the air to move around the torso relative to abrupt obstruction on the flat model. No. What do you mean the breasts? Are you saying the breasts are acting like an airfoil? Are you saying no? Are breasts airfoil shaped? Are breasts vaguely airfoil shaped? No. Abrupt obstruction of flat model. The wordings. No. Lukowa's enormous melons are air. No, this was a setup from the beginning. The moment they chose the boundary conditions, they knew what was gonna happen. No, this cannot be. This further exemplified in figure 12, which shows a set of horizontal streamlines. In 12A, the air flows smoothly atop the breasts, whereas at the flat model simply forces a relatively large portion of the incoming air to stall at the torso. No, what do you mean it stalls at the torso? What do you mean it just stalls at No, first stage of creep denial. Go puppy. No, they put They put the boundary conditions at the wrong side. They put it at the wrong side. Instead of the X, they should have put it at the Y wall. This was a setup. I can't believe this. The smaller circulation region prevents a small portion of air from surrounding the shoulders and instead redirects air downwards and off to the sides of the torso. No. It is interesting to note that the smaller circulation region directly atop the breasts, which is most likely dependent on the angle between them and the chest, from what can be seen in 12A. Figure 3 provides an upwards facing view of the models along with horizontal streamlines. Air flowing beneath the bust gains a velocity that is approximately 20% higher than the mean free stream velocity before being diverted perpendicular to the body and interacting with the incoming air and the rest of the torso. By the action of the breast, the air that is diverted in such a way that it is able to maintain momentum while it moves around the rest of the chest. This is in contrast to 13B, where a portion of the air is forced to stall in front of the chest before being redirected. Cope opinion. No. Figure 14 compares the velocity magnitude of the weight behind the two models at 5 different C locations. At these locations, the data is sampled along a line centered at a midline. And spans downstream from -1 and -2 meters. The Z locations are taken at heights of 0.1, 0.5, 0.9, 1.18, and 1.55 meters, all of which correspond to feet, legs, hips, chest, and head. From this comparison, the differences in wake velocities are slight, with the only significant difference occurring at the height of the legs. At this height, it can be seen that the flat model has a wake velocity that is consistently higher than that of the normal model. This observation can be attributed by the lower energy present in the vortices generated by a flat model. These weaker formations are affected by the mean flow to a greater degree, and thus the velocity magnitude in this region is higher than if the vortices were to have greater strength, as seen with the normal model. Okay, we're at turbulent kinetic energy now. Figure 15 shows a slice of the domain through which the median plane of the models, indicating the TKE present in the flow. At first glance, contours for both models present the same general structures as described earlier, such as the PRR behind the torso and the smaller structures associated with the legs. Due to the automatic scaling of the colors, the differences present in the PRR of the flat model compared to the normal are slightly exaggerated. However, the differences are still distinguishable in that the PRR for the flat model has a measurably higher level of TKE than that of the normal model. Indeed, B indicates that the two apparent bands of significant TKE associated with the PRR are generally more intense, even after factoring the differences between the color scales. So no, what do you mean? The turbulent kinetic energy is more intense in the flat model? What do you mean? This lower band with the PRR was found to be more compact for the more normal model, whereas the flat model had a marginally less intense and more widespread band. This effect may be attributed to the way the downwash from the hair interacts with the PRR. Directly below the PRR is okay, so here we have, so it's inverted, the color. So basically the blue is the highest. No, what do you mean? Why is it more blue? No. Directly below the PR is the T. Okay. Present in the vortex pairs originating from the legs. In 15A, the normal model has notably higher level of TKE associated with these vortices, coupled with the observation that this energy is maintained as the flow advex downstream. In contrast, 15B shows that the TKE in the vortices is lower and that the energy dissipated sooner. This remark further supports the interpretation hitherto that the formation of stronger vortices, the normal model generates play a role in reducing both drag and lift by diverting energy away from the PRR. All that blue is actually so over. Smaller regions with notable TKE present between both models are those associated directly behind the legs at the ankles and directly above the rim of the baseball cap. Between the two, the TKE at the ankles remain unperturbed by the differences in the wake structures above it. This region is related to the individual wakes associated with each foot, behaving much like the two-cylinder arrangement as described earlier. A downward jet of TKE originating from the thighs and curling parallel to the mean flow direction at the height of the knees shows some variability between the two models. This region is linked to the jet of air that is formed between the legs, interacting with the downwash of the hair. With the normal model in 15A, this jet of turbulence remains both vertical and closer to the legs. In 15B, this region takes on a slightly more horizontal transition and extends farther into the wake. A small circular region, much like that associated with the breasts on the normal mode, is found above the brim of the baseball cap, which is due to the blunt transition to the shape of the head imposes to the incoming flow. Finally, somewhere with less behind the breast. No. Comparison of TKE at 5Z locations. Okay, so how are we comparing the normal and flat? Oh, the flat ones are the dotted line ones. So the dotted line. So it actually depends where. It actually depends what portion and which one's higher. Figure 16 shows the TKE around the torso of both models along the coronal plane. As obvious as the difference between both models, the presence of turbulent region behind the breasts and below the axilla comes as no surprise. It is apparent that this region is influenced by the small recirculation region that forms above the breasts, spilling air downwards and behind the torso, which can be seen in figure 12. Furthermore, air from beneath the breasts also contributes to the size of this region, as in figure 13. It can be understood that this layer of accelerated air provides additional shear against the flow from above and increases the turbulence behind the breasts. Since the flat model lacks such features, presents an understandably unremarkable result with only a small sliver of turbulence along the side of the torso. I think it's this one. Yes. Yes, so somewhere where the flat model wins. Look at this. Look at this. There's no turbulence here. Look at it. Yes. Yes, this is the only result. Ignore every other result. Only figure 16. Yes. It's called grasping a straw. P. Common to both models, however, is turbulence being generated by the hair itself, stemming from the hair being left yes, stemming to Lokowa using hair gel. Lots of hair gel. The true extent of how much turbulence is generated from the solid hair and its effects on PRR is unfortunately intractable from this current study due to its highly complex geometry. Though it is expected that simulations dealing with physically accurate hair may undoubtedly increase turbulence and hence drag based on casual observations done on how hairstyles can affect aerodynamic performance. The same approach used to obtain shave your head. Yes, the same approach used to obtain information as seen in figure 14 was used in figure 17, with TKE being measured instead of velocity. As indicated from this figure, it is seen that the vortices originating from the legs indubitably. This guy likes the word indubitably, diverts energy away from PRR and supports the findings stemming from figure 15. Valdebenia, please. I already posted a picture of Valdebenia. I already tweeted a Valdebenia picture. Indubitably is a good, but I've never read it in a science paper, and then it's this guy likes using it. This is reflected with a stronger overall turbulence present at Z locations corresponding with hips, chest, and head for the flat one. It's indubitably a good word. But yeah, it only makes me think of, it just makes me think of the detective. Slight differences are noted with the flat model having a higher peak TKE at the legs immediately behind the body than the normal model. Then from 1 to 2 meters downstream, the normal model generates a greater amount of TKE. This observation may ultimately be attributed to the difference in shape the leg vortices assume between the two models. Oh my god, we're at the last. We're near the last page. We've read 11 pages. I can't believe you. Why would you sit through 11 pages of science as evaluation for the effects of macroscopic geometry between the two models on skin friction is shown with figure 18. What is this figure represents a scatter. This figure represents a scatter plot of C, measured at every vertex on the models, with regions of relatively high C sub f labeled according to which location on the model they are found on. Two directions are evaluated, with the x-axis on A representing the streamwise position and the x-axis on B representing the Z location. So the Z, that's the height location. X-axis is like the flow. Okay. See, they should have put the boundary conditions. They should have put the symmetry and the pressure outlet at plus y and negative y boundary. I can't believe they put it at X. They set up this author is such a flat is justice hater. I can't believe they set up for failure. It's great to have both the theory understanding being supplemented with a live visual demonstration. You've been looking at the same thing. Maybe even be biologist. You're a man of science. You have no choice. You're so smart now. Expectedly, both models feature the same general scatter plots, with nearly negligible differences. However, common to both models and the plots are the presence of numerous spikes associated with the hair, inasmuch as they are an artifact of the hair being modeled solidly. These spikes are aptly denoted as hair anomalisms within the plot. As such, the hair is undeniably a major contributor to skin friction in both models. So skin friction coefficient and downstream location, and Z location is the height location. So the skin friction coefficient, yeah, the highest is hairs. Where's the feet? ankles. With the source of skin friction being contributed solely by the hair from the rear of the model. Another exemplification of the hair's effect on C sub f can be seen as 18, with a grouping of peaks obtaining a value of 0.06 corresponding to the hair tips and bangs around the face. Additional sources of C sub f can be easily observed in the same figure, such as the ankles, around the thighs, the fingertips, and especially the Koa's horns. These dramatic changes to skin friction indicate where on the model flow separation is more likely to occur, which in turn relates to where turbulence can potentially be generated. The breasts, compared to the relatively noisy scatter generated by the rest of the body, provides a smooth transition in regards to skin friction over its surface. A small spike can be found at the downstream location of y equals negative 0.77 here, which corresponds to the small recirculation region above the breast seen in figure 15. In a sense, it can be deduced that the breasts act to reduce C sub f, which can be seen as a small dip in the smoothed data centered around Z equals 1.2. However, with such a diverse of a plot, the average C sub f across the whole body can be seen as roughly 0.01 from both figures, which indicates how little skin friction actually affects overall drag with bluff bodies. Summary and recommendations. This paper has offered a unique compendium, yes, a very unique compendium of data indeed, providing insight into the effects of a specific physiological feature. Yes, a specific physiological feature. What feature could that be? On the aerodynamic performance of a human. As such, the results have indicated that large breasts can be notably aerodynamic. No, it was a setup. It was a setup. They used the wrong boundary conditions. The flat model incurred a 4% maximum drag increase compared to the normal model, with an average of approximately 2% spanning velocities from 1 to 30 meters per second. The flat model also experienced more lift, with the maximum difference being 32% and averaging 22%. As illustrated, the mechanism behind the drag and lift behaviors observed between both models was elucidated through the analysis of streamlines around the body. The structures associated with TKE. The normal model provides advantageously lower drag and lift. No, it was a setup. I can't believe this. This was a setup. I can't believe this. The anatomical difference is a slight increase in aerodynamic performance when walking through water, which goes real life Uber record. We need to know it. From what has been presented in the preliminary work, it is safe to conclude that the phrase flattest justice is deficient aerodynamically. No, what kind of phrase is this? What kind of shit is this? I can't. They set up this. Shut up. They set up this. This is a setup. No, this is a setup. They put the symmetry at X, boundary condition symmetry at X, and then they put like the pressure outlet at negative X. If all they have to do change their boundary condition. All they have to do is put it at the other side. You can't just do this. You can't just do this. It was a setup. They just have to put the airflow. You just have to put the airflow. You can't do this. They just have to rotate the airflow 90 degrees. Care to do your own research? You just give me this simulation file. I'm just going to rotate the flow inlet so that it will flow through the sides instead of the front. Like, can just give me this. Give me your ANSYS simulation file. Give me your freaking ANSYS simulation. This is a setup. Like, look at this. Look at this. Like, the outlet. So, oh, I was confused. I said a while ago the symmetry was in yellow, but this is inverted. Oh, sorry, I was wrong. Symmetry is supposed to be the ones where there's no outlet and inlet and there's no exchange occurring. So this is the inlet. So the yellow is blue. It's now yellow. The outlet is in red. It's now blue. So you just have to put the inlet here. Just put it at the side. Just rotate your domain. Just rotate your domain 90 degrees. Rotate it 90 degrees, and you know what will win? You know what has higher drag? The big boobs. You know why? Because you will hit boobs, and you know what it will hit in the flat model? Nothing. It will just go through. It will just go through straight. Look at it. Just get this inlet and put it here. Just get this inlet and put it here. Just put it 90 degrees. It's under acknowledgements if you really want it. Is it? Call alarm. Let's do a completely different test. It depends. What if you're like, okay, if you're running in the Olympics, fine, the air is going this way. But what if you're skiing sideways? Okay, what if you're running sideways like a crab? You know, like a crab running sideways. What if it's like that, huh? Ever think about that? You're running sideways like a crab, huh? I bet you didn't think about that. This snowboard. You're snowboarding sideways. A major shortcoming intrinsic to the study was the decision to leave the hair present on both models as immovable and solid. As noted earlier, yet they should have shaved her, was captured by the geometry of the hair, and this affected the wake structures behind the model. This effect therefore blunts the overall applicability of the results found in this study to actual human models. It is important to note that large breasts do give a consistently notable aerodynamic advantage, as reflected in overall lower forces experienced by the normal mode. No, I'm gonna throw this away. No, I'm gonna throw this away. No, I'm gonna throw this. I'm gonna throw this away. I have no need for this. Throw it away. We don't need that. We don't need that in our lives. We don't need that. We don't need to have that in our lives. We're slow, man. Bye. future study, several recommendations are provided. In the near term, a re-evaluation of current work without the hindrance of model hair should be done. Work using a time-dependent computational approach, yes, to a transient simulation. Ideally, this experiment would use live subjects of varying breast sizes. Yes, yes. Hello, I would need some volunteers of varying breast sizes. Any crash on Sayonara fight? The author would like to send a massive thanks to Ice Omega for the Quetzalcoatl model. Would like to make a shout out to users that our anime IRL and our anime memes for their inspiration. That's so unfunny there. No, my respect is dropping. No, like I tried to go here before, and then nothing was funny. Maybe it's changed now. Maybe it's funnier these days. Let's check it. I'm gonna check it. I'm gonna go there now. I'm gonna see. I'm gonna sort by. Give me your best. Sort by best. Sort by best. Sort by top. Sort by top this year. Give me your best this year. Well, it's not funny. This is the top. I sorted by top post this year. This is it. This is the funniest thing they've had this entire year. This is it. This is the funniest shit they've had this year. I sorted by top this year, and this is what they have. This is what they have. Where's it? This is it. This is it. This is their best. This is the best they got. This is their funniest meme of the year. This is their funniest meme of the year. It has 54,000 upvotes. This is it. This is it. This is it. It can't get funnier than this, guys. Nothing's funnier. They cannot. This is it. Oh, it's so funny. The 2018 wasn't as bad. I have no idea. War crimes is the funniest shit I've ever seen. Additionally, our anime are coming up for the inspiration. Lastly, the author expresses gratitude towards Kyo Shinshan Kyoto Animation for their work on Miss Kobayashi's Dragon Maid. The author received no funding for this research. The results of the present study do not constitute endorsement of any potential entity, whether expressed or implied. Quetzalcoatl is also not the author's waifu. It's not. Why didn't you use your waifu? Though he respects her character as the goddess of sick. Yes, like Rura has mentioned, a goddess of sick. Oh my god, the generated data. There's some. Is this still alive? Is this link still alive? How do I copy link? Is this mega link still alive? No, it says no longer available. The file is no longer available. It's not even here anymore. But yeah. It's not even here anymore. I can't believe you. It's almost 4 hours. I can't believe you watched. I can't believe you wasted so much time listening to me read how many pages? How many pages was this shit? 12 pages scientific paper. Are you happy with how you've spent your weekend, huh? Are you happy with how you spent your weekend? You've gained knowledge, and knowledge is power. Yes. Infinity is your favorite dish. Yeah, thank you for spending time with me when I. Oh no, how do I undo my angry face? Where did it go? Where did it go? Oh, there it is. Yeah, thank you for spending so much time with me, even if I just wanted to read a scientific paper. No, before watching. Thank you so much for keeping me company. You'll probably end in a while, so thank you so much. I appreciate it that you gave me your time, even if a lot of it was just walls and walls of like text and like, you know, engineering physics terms. Yeah. Is the stream dying, or is that just me? Is it? Oh my god. Oh my god. Oh no. Did I disappear? Did you guys not hear everything I said? We're back. I really should like monitor the stream, but I'm lazy. I'm lazy. I'm sorry. But yeah. Thank you so much for watching, keeping me company. Like I like reading. I actually wanted to stream today, but I had no idea what to do. And whenever I have no idea what to stream, my brain defaults to cursed scientific papers. Thank you. Also, what is this? That is so cute. Thank you. Thank you. Thank you. Thank you. You're so fast. Thank you. Please look at this. Please look at this link that animal. Please look at it. Please admire it. Please admire it. Yes, I like the pose with the glasses. That's my smart pose. That's exactly my smart pose. Yes. Thank you. Thank you. Thank you. Where are you taking me? Yeah, thanks for. Yeah, and I won't make so much nice art and then depriving the public by not posting them of nice art. Yeah, There's so much nice art that's being deprived, that the public is being deprived from. Oh, yes, now's a good time, I guess, to show off, brag about all the nice stuff I got today. And yeah, before I go, so it's in order of we got them today. So this one, wait, where's my share folder? This one, maybe you saw this already, but this one's the one from Breast. My stream player died. Oh, is it gone again? Is it gone again? Is my stream disconnected again? No, it was just me. Oh, okay. Oh no. No, it's not gone for me. It's all good. Okay. I'm sorry. I should be learning to monitor this. But sorry, I was lazy and I never monitor my streams. Yeah, look at these two. Sorry, there gonna be a white warning if you're in a dark room and your phone will suddenly become white. Look at this one. Look at it. It even has my cow. It even has my cow. It even has my cow. It's amazing. Wait, where's my cow? Hold on, I have to put back my cow. Whoops, that's too large. Whoops. Yes, my cow. Yes, my cow. Where's the cow? Cows are cute. Must rock your beloved. Yes, and there's not even one. There's two, and I like how they did the separation of the tail. It just looks cool, simple as. And I like how they included the cow because I love cows. I love cows so much. Like, whenever people see cows, people who know me in real life, they remember me. Because whenever I see a cow, I'm like, cow. Even if I see cows every day, whenever I see cows, I'm still like, cow. I really love Must's style. I mentioned before, I like stylistic stuff, and they're like, stylistic to the max. Yes. And then this is the other one. This is the other one they made. It's so cute as well. Like, I love how they draw expressions as well. Like their faces are never boring. They always have an expressiveness in their face. Yes, it's super cute. And then this one, oh, you said I could share them. And you said I could, so I will share. Even wait, where's I need to see where I saved the. Yeah, I want to share them for, but yes. Putting in the share folder. I mean, I'm sharing even this is this one. Look at this. Look at this. Look at this. Super cute. Super cute. Thank you. I love the pose. I love the yes. That's smug. Yes. I love the pose and I love the proportions. Like it's just this is like the proportions of anime girl that I find. It's like super extra cute. It is good. It reminds me of like the Little Mermaid pose. Yes, and thank you for getting the torso shape right. Yes. It misses something to be aerodynamic. No, they did a stud. No, I'm aerodynamic in the water. No, you don't understand. When you're in the water and you're swimming, you're not swimming like while in a vertical position. You're like become straight like a bullet. You know, I'm aerodynamic that way. And it doesn't apply to swimming. The study doesn't apply to swimming. And then there's these sketches too. Like look, it's super cute. Like I'm happy about because like you can rarely see my back, but I'm proud of like the back design with the lobes, and you can see it here. And then there's me doing the middle finger because if you watched my debut stream, I kept doing the middle finger. It's to show off the accuracy of finger tracking, not because I think you deserve it, even if maybe you do. Who knows? I don't know what you did. Maybe you probably did something bad in your day that warrants someone flipping you off. Like, I don't know what you did. I'm not stalking you. I don't have a camera in your house. Hydrodynamics. Is it aerodynamics? You can't swim in an pose. Okay, like that's so intimidating. Imagine like someone approaching you at max speed and they're just like in a vertical A pose. Like that's like a horror movie. So flat is the most hydrodynamic. That's right. So cute. It is so cute. And then Swas the one from today. This one's like my first design that I made with this is also by Enne. It's the first design I made where I still had cat ears because it's opabinya, right? It's nya. Yes, my first design, my PNG had cat ears, and then I had knobs, and the only reason I don't have knobs is because I am lacking the modeling expertise to add them, but I really want them. But yeah, it's so pro, like foreshortening, and like the pose. It's like yeah, and it's so it looks like a wallpaper. Yes, but one is a design for being hugged by many legs. Yes, that's yes, being hugged by all the legs. And we're rapidly approaching an acacia at 10 meters per second of pose. Yes, be intimidated by me. 3 centimeter creature resting on your head. 7 centimeter. Where's the warning? Where's the slander? Send warning. Yes, imagine the crawling sense. Yes, so isn't that like, why would you hug a normal girl when you can't even feel their little knobs crawling all over you? Yes, you need more appendages for extra hugging power. Like, the more appendages, the more hugged you are. Yes. Yeah, thank you so much for oh wait for the art. And yes, I really love them. I will treasure all the art forever. Thank you. Yes, I will treasure all the art forever, including this one. Yes, this is the art to be treasured. Yes. Yes, it's hard to talk about. It's hard to say anything. I feel like it explains itself. Yes, there are 2 big spheres, very spherical and very anatomically representative of the Opabinia anatomical parts as found in the fossil discovered in the Burgess Shale by Walcott. Yes, back in the early 9. No. Oh, no, the 8 equals C. No. No, that is so good. No, why is the truth? Why is the truth? It's not slander if it's true. But yeah, thank you. Yeah, thank you so much. I'll probably end in a while. Thank you so much for giving me your company and your time above everything, while I'm doing just something I wanted to do on my own. Like, but instead of doing it on my own, I get to do it while people are spending time with me. So thank you. I really appreciate it. I'm just really concerned that it's sapping your sanity to spend like more than 3 hours with someone reading the scientific paper. But thank you, and thank you for the art as well. Thank you. I love them all so much. Thank you. Oh, Vivi, I never asked you if I could show, because the one you made too before, it's like the first ever one, so it's extra special because you're the first ever one who who gave me a drawing. Yes. You can show. Okay, wait, it's in a different folder. It's in this folder. Okay. Ta-da! It's when I was still deciding. I'm sorry, I casually said goodbye and now I'm sure. But yeah, it's the first ever one I got, so it's super extra special. It's when I still had cat ears as well. And it's when I couldn't decide where to put my eyes yet. Because like the Opabinia eyes are on stalks, right? That's why this one has the eyes on stalks. Because I still haven't, because I wanted it to be like an Opabinia with the eye stalks. Yeah, it's super cute. It's special because it's the first one I got. Thank you for this one also. Thank you. Thank you. Yeah, good night or good morning. Good afternoon. Thank you. Oh, thank you for everything. Thank you. Thank you, Seiki. Thank you. I'm happy you're here. I'm happy you're here too, Third. And Rura, thank you. I'm happy you're here too. And Sakamoto-san, thank you. I'm happy you're here. And good morning, everyone. Yeah, you went to have breakfast. I remember. Thank you. I'm happy you're here as well. And Vivi, thank you. I'm happy you're here. And then I'm happy you're here too. Oh my god, did I miss anyone? I didn't miss anyone, right? But yeah, thank you. Thank you for spending so much time with me. Thank you. Thank you. Thank you. See you. Thank you.